Hello there and welcome back to the Science Sleepy Minds. You're standing in the quiet dark of an alien plane. Above you hangs a star, not blazing gold, not crisp white, but a deep ember red. The world feels hushed, like twilight has settled in for eternity. The plants here are strange, black as obsidian, wide-leafed, spongy underfoot. They don't need much to live. In fact, they've evolved to thrive on the faintest glimmer of warmth and light, the kind that barely seeps from their lazy crimson sun. You've landed on a planet orbiting a red dwarf star, the most common kind of star in the known universe. These things are tiny by stellar standards, often just 10% the mass of our Sun, but don't be fooled, they're stubbornly long-lived. While our Sun has a lifespan of around 10 billion years, a red dwarf could simmer for trillions, outliving galaxies. So if any kind of life takes root here, it gets time, loads of it. Now here's your cold reality check. You probably wouldn't survive 5 minutes on this planet without heavy gear. The star isn't hot enough to warm a world the same way our Sun does. To be habitable, this planet has to orbit very close, often 10 times nearer than Earth orbits our Sun. That proximity creates some awkward gravitational consequences, but more on that in a minute. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Let me know where you're listening from, and what time it is in your part of the galaxy. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You walk along the edge of a marsh lit only by the faint red overhead. Shadows are thick and blurry. The sun is barely distinguishable from a glowing coal in the sky. You could look straight at it without flinching. This world orbits inside what astronomers call the habitable zone, the sweet spot where liquid water might exist. But the conditions here aren't sweet in any familiar way. Plants have evolved not just to drink in every rare photon, but to hoard them. Their leaves are dense and hyperpigmented, likely black or deep purple, to soak up the full spectrum of feeble starlight. Photosynthesis here is a slow, delicate game. Instead of racing to capture light before the sun sets, plants sip from the dim pool all day long, because the day might last weeks. Here's where it gets strange. Planets this close to red dwarfs are usually tidally locked, which means one side always faces the star, while the other remains in darkness forever. On the star-facing side, things might get warm enough for liquid oceans. On the dark side, it's an ice desert. You're probably standing somewhere near the Terminator line, that narrow, habitable strip of constant dusk circling the planet's waste. Life clings here. The atmosphere could be thick, maybe even foggy, needed to help circulate heat and prevent one side from freezing while the other bakes. Winds howl endlessly, trying to balance the eternal cold of the night side with the dim warmth of day. The air tastes metallic, tinged with volcanic gases. You can almost feel the pressure on your ears. You notice a bulbous creature sliding by on jelly legs, bioluminescent markings flickering in rhythmic pulses. It seems photosynthetic but also predatory. Out here, survival might demand a little of both. Energy is a precious currency. The most successful organisms might hoard multiple strategies, harvesting light, consuming organics, even breaking down minerals for chemical sustenance. A few evolutionary biologists theorize that chemophotosynthesis might thrive in these environments. Creatures who sip light when they can, but rely mostly on digesting inorganic compounds, and they wouldn't rush. There's no evolutionary pressure for speed when your sun shines in permanent molasses time. You find yourself under a towering arch of fibrous vines. They hum faintly. The plants here might communicate chemically through airborne pheromones or soil signals. With such a low-energy environment, speed is costly, but complexity isn't. Historically, we used to think red dwarfs were a bust when it came to life. Too unstable, too faint, too boring. But in 1995, that all started changing. Astronomers discovered that Proxima Centauri, our closest stellar neighbour, just over 4 light-years away, is a red dwarf, and it has at least one rocky planet in its habitable zone. Since then, dozens more red dwarf systems with potentially Earth-like planets have been spotted. Here's the catch. These stars flare. Violently. A red dwarf might go quiet for weeks, then suddenly vomit X-rays and ultraviolet radiation strong enough to sterilize the surface. That creature you saw earlier? It probably evolved under threat. It might have mirror skin or subdermal pigment sacs that reflect lethal radiation, or maybe it hibernates during flares, burrowing into soil or diving deep into oceans until the tantrum passes. Some astrobiologists debate whether life here would ever emerge at all. Historians still argue whether solar instability prevents early biology from gaining a foothold, or if life might evolve despite it, even using the chaos as fuel for innovation. After all, Earth itself was a violent mess when life first crawled into being. You reach a ridge. Below, a shallow lake stretches toward the red glowing horizon. Strange, rootless reeds drift across the water's surface, lazily drawing in sunlight with fluttering fronds. The lake's edge is lined with silicate crust, maybe even a sign of ancient hydrothermal activity. If this world began like Earth, volcanic heat might have jump-started life long before the sun ever got involved. As the air cools and the hum of plants rises again, you get a sense that time means something different here. Decay is slower, growth is quieter. Civilizations, if they ever arise, might stretch their lives across centuries, evolving not speed but patience. It's a world designed for endurance, not drama. Of course, all this depends on whether that pesky stellar flare doesn't show up tomorrow and fry the whole biosphere. But that's the gamble when you live under a red dwarf, a lifetime of stillness, punctuated by sudden violence. You lie back on the sponge grass, eyes on the red star above. It's not much, but it's enough. The air shifts. It's barely perceptible at first, a kind of dry shimmer across your cheeks, but then it hits you like a wave of static. Gone is the soft, dusky glow of the red dwarf. Now, the light is bluer than anything your eyes evolved for. So blue, it's nearly white. Blinding, as if the sky cracked open and poured pure fusion straight onto your face. You've arrived beneath a blue giant, one of the rarest, hottest types of stars in the known universe. These aren't just suns, they're monsters 10 to 20 times more massive than our own, shining with the fury of 1,000 ordinary stars burning through their hydrogen, like a college student tears through ramen on finals week. And like that student's sleep schedule, blue giants are unstable, short-lived, and likely to collapse spectacularly. From your new vantage point on a rocky plateau, you gaze upward, and then quickly look away. You physically cannot stare directly at the star. Even filtered through this alien planet's atmosphere, the radiation is intense. Blue giants bathe their systems in harsh ultraviolet light, extreme heat, and frequent gamma-ray bursts. On Earth, we wear sunscreen to fend off our modest yellow sun. Here you'd need an entire suit of armour, or maybe an exoskeleton made of reflective crystal scales. And yet, life might still find a way. Maybe not in the classic tree-hugging, ocean-swimming sense, but in something sleeker, faster, and weirder. You crouch behind a thick, glistening formation of rock, volcanic glass possibly. The terrain is scorched, and the horizon shimmers with thermal haze. Even in the cooler shadows, the ground radiates heat like a stovetop left on simmer. Whatever lives here doesn't just survive the sun, it has to outrun it. Biologists speculate that life on such worlds would have to evolve speed. Cells would replicate rapidly, heal instantly, and shut down just as fast in self-defense. Maybe metabolism runs in overdrive. Creatures live for mere days, burning bright and brief, constantly regenerating from ultraviolet damage. What might that look like? Picture lizards with mirrored hides darting across obsidian sand, their blood rich with UV-absorbing proteins, or winged insects with kaleidoscopic wings that both reflect and refract light into dizzying displays, confusing predators long enough to escape into glowing cracks in the earth. Some theorize that organisms here wouldn't have melanin like us. They'd have evolved layered reflective cells like opals or fish scales to scatter incoming radiation picture peacocks on acid, armoured in living jewellery. But this place isn't just intense, it's unstable. Blue giants live fast and die violently. The lifespans of these stars are only a few million years. In cosmic terms, that's barely enough time to yawn. So here's the real kicker. If life begins at all on a planet orbiting a blue giant, it has to do so very fast. Historians still argue whether such fast-evolving systems could give biology a real chance. Could DNA-like molecules even form under such brutal radiation? Or would life here have to skip the whole carbon-based warm-up and go straight to something exotic, like silicon frameworks or liquid crystal matrices? Some fringe theorists even suggest that life might begin as radiation-resistant crystals, slowly self-replicating under UV bombardment until they reach complexity. It sounds outlandish, sure, but the early 20th century thought life couldn't survive without oxygen, and then tardigrades laughed in our faces. You notice a movement on the horizon, something tall and stilt-legged, moving like wind in cloth. It doesn't walk exactly, more like it flows. The sun strikes its surface and it shifts colour from silver to deep blue, as though it's cloaking itself in the wavelength least visible under this light. Camouflage here wouldn't mean blending with plants or rocks. It would mean managing reflectivity. Hiding might require turning invisible to the spectrum itself. Creatures could evolve tunable surfaces, like sunglasses that adapt instantly to solar flares. Speaking of which, boom! A sudden ripple through the air. You glance up just in time to see the sky flash. A coronal mass ejection. Nothing too catastrophic, but in real life, it would release a shockwave of charged particles deadly to unprotected life. Earth's magnetic field shields us from such bursts. But here, you'd need a planetary-scale umbrella. Maybe the planet has one. A supermagnetosphere generated by a metallic core spinning like mad under tidal forces. Or perhaps life has taken the opposite route, living deep underground beneath layers of mineral shielding, emerging only during the quiet solar hours. Oddly enough, some blue giants have been found with disks of dust and gas, the nursery signs of planet formation. One such star, Zeta Ophiuchi, races through space at incredible speeds, leaving a trail of shockwaves in the interstellar medium. It's not exactly the neighbourhood you'd choose for a quiet garden planet, but say, just for fun, that one of those disks did become a rocky world in the habitable zone. A tight, precarious orbit where temperatures don't instantly vaporise water. Could an ecosystem survive here long enough to leave fossils? The best guess? Not in the way we imagine. Evolution here might favour ephemeral intelligence, fast-growing, fast-learning species that pass knowledge genetically or chemically. Instead of relying on long lives, picture a creature born with memories. Entire cultures built in under a month. Civilizations that bloom like orchids and vanish before their star even hiccups. And if a planet in this system had multiple moons, you'd get complex tidal patterns, perhaps enough to create pockets of habitability in low-lying basins or deep ocean trenches. Life might huddle in cooler craters, developing small mobile biomes that migrate across the surface like land-based coral reefs. On the fringe of scientific thought, there's even the idea that life on blue giant worlds might become spacefaring early. Not out of ambition, but necessity evolve, build, escape, before the star explodes. Because that's the end game. When a blue giant dies, it doesn't go gently. It collapses into a supernova, blasting its outer layers into space and leaving behind either a neutron star or a black hole. If anything lived nearby, it would be vaporized, memory and all, so why bother imagining life here? Because even the most hostile, short-lived stars might spark something, and in those fleeting millions of years, a kind of beauty could emerge that never needs to last forever to mean something. You lie low as the light dims again, temporarily, a rare lull in the chaos. The stilt-legged creature turns its mirror face toward the horizon, soaking in the last safe rays of the blue beast above. It doesn't run. It doesn't need to. It's already lived 5 lifetimes this week. You're lying in a wheat-coloured field now, except it isn't wheat. The stalks are too thick, too rubbery, and every so often they quiver as though hearing something you can't. The sky overhead is clear but strange, with 2 suns trailing each other across the heavens, one large and golden, the other small and orange, just slightly behind like a reluctant sibling. The light they cast is layered, like 2 competing playlists playing at once. Welcome to a binary star system, where planets don't just orbit a sun, they waltz in a delicate gravitational ballet between 2 of them. You're standing on a planet that's pulled between not 1, but 2 centres of light and heat. It's beautiful, yes, but it's also wildly unpredictable. The air is warmer than expected, but patchy, like stepping through invisible currents. And the plants? They're directional, but confused. Some leaves twist toward the larger sun, others toward the smaller. The result is a sort of biological improvisation. growth patterns that reset daily, vines that chase one light in the morning and another by afternoon. Binary star systems come in a few varieties. In some, the two stars orbit each other closely, and the planet orbits them both. Imagine a planet tracing a wide circle around a swirling fireball duet. In others, the stars are farther apart and the planet orbits just one, with the second sun rising and falling at odd intervals, like a surprise houseguest with no fixed schedule. You happen to be on the first kind, a circumbinary planet. Now this isn't just sci-fi fluff. We've actually discovered such worlds. Kepler-16b, lovingly dubbed Tatooine for obvious reasons, is one of the first confirmed planets in a binary system. It's not Earth-like, more of a gas giant, but its mere existence proved the concept. Planets can form and can persist in the gravitational chaos of binary stars, but persist doesn't mean coast along calmly. The big problem here is instability. Light levels fluctuate as the stars orbit each other, seasons are irregular, temperatures swing wildly, depending on where each sun is in its dance. A summer might last 20 days or 3 years. The growing season? Unpredictable. Rain cycles? Don't even try. So what does life do when it can't rely on patterns? It adapts. Fast. You wander toward a rocky outcrop and find a patch of clustered fungi-like structures, plump, translucent domes, each about the size of a football. As one of the suns dips behind the hills, the domes darken, retracting tendrils into the soil. You hear a faint clicking, like glass beads tapping together. It's communication maybe, or just chemical hydraulics, resetting for the next solar alignment. Here, organisms likely evolved to be hyper-responsive. Their biology isn't tied to fixed seasons but to the relative position of their suns. Instead of spring or fall, they respond to solar angles, light frequency shifts and magnetic pulses. Imagine migrating animals that track not geography, but stellar geometry, moving only when both suns align a certain way. Photosynthetic life has it even harder. With varying wavelengths and intensities, plants might develop layered pigments, each tuned to a different part of the spectrum. When one sun dominates, they unfurl red-absorbing layers. When the other takes over, blue-absorbing pigments rise to the surface. The process looks like breathing, light breathing. Fringe botanists have speculated about chromaflex plants, organisms that literally change colour depending on the dominant sunlight, like a forest of slow mood rings. These wouldn't just survive under dual stars, they'd depend on it. Maybe certain reproductive cycles only activate during dual sunrise, a rare event like a solar full moon. And then there are the predators. You hear it before you see it. A low, whirring pulse that vibrates in your chest. A creature moves along the ridgeline, walking sideways. Not crawling, not flying, gliding somehow. Long, flat limbs stretched wide like solar panels, absorbing every photon before the light shifts again. It stops and flares a series of membranes along its spine, orange for one sun, violet for the other. You realize, with a shiver, that it's not choosing between them. It's feeding off both simultaneously, its metabolism switching mid-motion depending on which wavelength is stronger. Now there's a historical twist for you. In the 18th century, scientists still believed all stars were singletons, self-contained suns like ours. It wasn't until William Herschel discovered binary pairs in 1802 that our view expanded. Today, we know that more than half of the stars in our galaxy are part of multi-star systems, meaning if life is out there, it's statistically more likely to come from a system with multiple suns. But of course, there are debates. Historians still argue whether binary systems allow stable enough climates for life to persist beyond microbial forms. Some simulations show planets getting yanked into eccentric orbits, too hot one year and too frozen the next. Others argue that if a system is wide and slow-moving enough, things can mellow out. Not Earth-level mellow maybe, but manageable. You walk now through a shallow canyon, its walls glittering with mineral deposits. Light bounces in from opposite angles, creating patterns that shift as you move. No shadow ever stands still. Animals here likely see in polarized light, able to pass out direction and intensity from two different suns. They might have dual pupils or rotating lenses. You wonder what you would look like through their eyes. Just another light-stained shape flickering with solar residue. At the canyon's edge, a pond shimmers with oily blues and greens. You dip a hand in, cautiously, and find the water lukewarm. On its surface float flat hexagonal pads, each one twitching faintly. They're photosynthetic too, no doubt, but they seem to be storing energy rather than using it immediately. Smart. These organisms probably evolved to bank sunlight, filling up during the rare overlaps when both stars blaze high, then coasting through the dimmer days. You sit back on a warm rock and let both suns wash over you. The larger one is setting now, dipping toward the horizon, while the smaller still clings stubbornly to the sky. Their light mingles, amber and rose, gold and lavender casting double shadows that stretch in opposite directions. It's chaotic, it's gorgeous, and it's alive. This world isn't predictable like Earth. It's a place where life evolves not for routine, but for resilience. Nothing here is guaranteed, except perhaps that something, somewhere, will always be adapting. You're sweating, but not from exertion. The heat comes from overhead and never changes, perpetual, unwavering, like someone left the oven on for the whole planet. The light doesn't shift. The shadows never move. There's no sunrise, no sunset. Just a dull, burnt orange sky that holds its position like a stubborn thought. You're on a tidally locked planet, one where a single side always faces its sun, while the other remains in permanent darkness. Like the moon facing Earth, this world keeps one hemisphere basking in eternal daylight and the other plunged in everlasting night. You stand now in the in-between, on the narrow twilight strip, known as the Terminator Zone, that wraps around the planet like a shadowy equator. This is where life might thrive. The sun-facing side, or day side, is an unforgiving desert of scorched rock, where metals might melt by midday, which, let's be clear, never ends. The dark side, or night side, is a frozen wasteland colder than Antarctica's worst mood. But here, in the narrow limbo between the two, something extraordinary happens. Balance. The ground beneath your boots is dry but not cracked. The air smells faintly of minerals and salt, proof that water, somewhere nearby, is still cycling. You step carefully, passing through moss-like growths that seem to breathe with the rhythmic pulse of wind. And oh yes, there's wind. The constant battle between blistering heat and bitter cold creates a never-ending jet stream around the planet's waistline, winds that can reach hundreds of kilometers per hour in the upper atmosphere. But here on the surface, things are quieter. Still dangerous, sure, but survivable, at least for the things that have evolved here. Plants in the twilight zone hug the ground. Tall growth would be a death sentence. The air pressure fluctuates wildly, and anything upright becomes a sail in hurricane-force gusts. So life stays low, flat, armoured, braced for impact. These aren't trees, they're light scrapers, like living shingles stacked to catch just enough light to photosynthesize without frying. The light itself isn't strong, it's slanted, indirect, smeared across the sky like a permanent golden hour. This calls for ultra-efficient pigments, deep purples, nearly black, engineered by evolution to trap every stray photon. You crouch beside one such patch and run your fingers along the edge of a leaf. It curls away, shy. Photosensitive movement, very fancy for a shrub. You see, time here is weird. With no day-night cycle, life has no natural rhythm, no circadian clocks, so creatures develop heat-tracking biology instead. Instead of sleep cycles, they follow thermal tides. When the heat dips a fraction of a degree, animals emerge to hunt, mate or drink. When the temperature spikes or drops too far, everything burrows. And speaking of animals, you catch a glimpse of something darting between rock formations, a quadruped, sleek and rubbery, with low-slung limbs and a pronounced thermal ridge along its spine. It doesn't have eyes, not exactly. Instead, it sports a lattice of reflective scales, perhaps tuned to infrared, allowing it to see heat instead of light. Out here, that's a much better evolutionary bet. Fringe theorists have imagined creatures that not only perceive temperature gradients, but communicate using heat pulses, like fireflies, but thermal. Imagine a pack animal flashing quick bursts of warmth through its skin to signal danger, food, or flirtation. It sounds strange, but we already have earthly analogues. Pit vipers, for one, who sense infrared radiation through facial pits to track prey. You wonder what an intelligent species might look like here. They wouldn't measure time in hours or days, but in thermal phases, the slight drift of the terminator zone over geological time, or the oscillation of heat across seasons, if the planet even has seasons. Buildings would be burrowed, half-sunken, insulated. Entire cultures could be migratory, perpetually chasing the optimal temperature ring as it slowly shifts due to axial wobble or atmospheric tides. That's the thing. This planet is stable in a chaotic kind of way. The sun never moves, but the air does, the heat moves, the chemistry changes, and life, as usual, adapts. Historically, astronomers used to dismiss tidally locked planets. The old thinking went, one side's too hot, the other's too cold, no way liquid water can exist. But then climate models started getting spicy. Around 2010, scientists began simulating thick atmospheres and oceans that could redistribute heat more evenly. Suddenly, these worlds didn't seem so hopeless. In fact, some researchers now argue that tidally locked planets might be the most common type of habitable world around red dwarf stars. Their stable orientation could offer constant conditions, something life actually likes despite the whole change or die vibe. Historians still argue whether those conditions are stable enough to permit complex life, but more and more it seems plausible. You continue walking along the Twilight Ridge, now nearing what looks like a small lake. It's not crystal clear, it's murky, maybe even salty, but it's liquid, and that's rare currency out here. Little polyps bob on the surface, some with thin filaments trailing below. They pulse faintly, opening and closing to draw in nutrients. Probably plankton analogues. Maybe the base of a fragile food web. You crouch at the water's edge and notice something glimmering below. Thin, ribbon-like fish twisting through the sediment, their bodies nearly translucent. Their muscles shimmer with what might be piezoelectric tissues, cells that generate energy from motion. On a planet where light is weak and food is scarce, maybe the act of swimming itself helps charge their biological batteries. You feel a breeze pick up, not a gentle one. This is a warning wind, the kind that precedes one of those global gusts that can strip soil off rock and fling pebbles like bullets. You retreat toward a low ridge, where thick fungal dome structures rise from the ground. Some are open, some closed. Emergency shelters, natural hibernation chambers. You slip into one. It smells like old rain and warm plastic. The inner walls glow faintly with bioluminescent threads, enough to see by but not enough to attract predators. As the wind howls outside, the dome closes, sealing you in. Here, you rest. There are no clocks in this world, no sunrise alarms, just you, and the sound of air pressure equalizing, and the low hum of an alien organism that evolved for a twilight that never ends. You're underground now, or what counts as underground on a planet that technically shouldn't exist. The walls are warm to the touch, almost alive, humming faintly with some buried force. A dim glow seeps through crystalline seams in the rock, casting flickering shadows along the tunnel as you crawl forward. Every few meters, you pause and listen. You're not alone. Because here, beneath a pulsar, nothing on the surface survives. Outside, the world is bathed in lethal radiation, blasted every few milliseconds by pulses of X-rays and gamma rays from a collapsed, rotating neutron star. These stars are the incredibly dense remains of a once massive sun that died in a supernova. What's left is a stellar corpse just 20 kilometers wide, but with more mass than our sun, and a magnetic field trillions of times stronger than Earth's. It spins rapidly, beaming electromagnetic death rays across space like a broken lighthouse on a warpath. And yet, you're here. Not on the surface, of course. That's a wasteland. If any original atmosphere existed, it's long gone, blasted into space. But deep beneath the crust, protected by kilometers of rock and mineral shielding, life might endure in the strangest of forms. The ground shakes faintly with each pulse from the sky above. It's rhythmic, almost musical. You stop to count, one beat every 0.7 seconds, fast enough that your nervous system starts interpreting it as something familiar, like a heartbeat, a planetary arrhythmia. Around you, small creatures skitter across the walls. Not insects, not exactly, but something in that neighbourhood. Flat hexagonal carapaces, with hair-like appendages bristling from every surface, they cling to the mineral seams, twitching as the pulse overhead reaches them. You realise they're not afraid, They're reacting, feeding even. See, some scientists have hypothesized that in extreme environments like this, life might evolve to use electromagnetic radiation directly, not as a hazard to avoid, but as a source of power. These creatures might be biological analogues to solar panels, but adapted for high-frequency energy. Instead of leaves, they've got crystalline plates tuned to X-ray or gamma-ray absorption. Insane? Sure. But then again, we already have extremophils on Earth that eat radiation, literal bacteria that feast on uranium waste, so it's not impossible, just deeply weird. You press forward into a large cavern and your breath catches. This place is enormous, like an underground cathedral sculpted by lava and time. Stalactites drip with slow amber ooze. Pools of thick liquid shimmer beneath you, glowing faintly with chemiluminescent organisms. The air is hot, metallic, and carries the tang of sulfur. Somewhere nearby, geothermal vents release superheated gas, the true engine of life here. This world, orbiting a pulsar, might be geothermally active thanks to residual internal heat and gravitational friction from other orbiting bodies, if it even has any. That heat could sustain hydrothermal ecosystems, much like the ones we discovered at Earth's oceanic vents in the 1970s. Entire food chains based not on sunlight, but on chemical gradients. Historians still argue whether a pulsar system could retain planets at all. The original supernova would likely have blown nearby planets apart. But there are exceptions. Take PSRB12, 57 plus 12, the first pulsar discovered with planets in 1992. Yep, planets, plural. The first confirmed exoplanets in human history were found around a dead star, not a living one. A haunting little joke from the universe. We don't know how those planets got there. Maybe they survived the supernova. Maybe they formed afterward, from debris. Or maybe they're captured wanderers, but they're there, and they orbit like good little corpses dancing to the ghostly beat of the pulsar. Back in the cavern, you crouch beside one of the pools. Something stirs below the surface. It looks like a ribbon, but thicker. A muscular wave that pulses through the thick fluid, generating faint electrical currents as it moves. You watch it rise, barely breaking the surface, and then dive again, leaving behind a few bubbles that pop with a faint luminous flicker. You get the sense it knows you're there. The creatures down here might have evolved to communicate via electromagnetic pulses. Brief, localized flares of energy that mimic the background radiation in timing, but not frequency. It's a kind of camouflage language. A way to talk without being overheard. Or maybe they've evolved to worship the pulsar. Not spiritually, but biologically. What if every beat from above is a kind of planetary metronome, guiding life cycles, feeding schedules, even reproduction? Instead of seasonal mating, they might have pulse phase coupling, synchronizing with radiation rhythms. A mating dance set to the tick of a dying star. You lie down beside the pool and feel the next pulse rumble through the rock. It makes your chest vibrate. It's comforting in a strange way, like knowing the planet still works, even if everything about it is completely alien. And then, something changes. The pulse slows, just slightly, but you feel it. The creatures react immediately. They stop moving. Every limb, every wave, every twitch halts in eerie unison. A pause, like breath held across an entire biosphere. This might be what passes for a solar eclipse here, not of light, but of signal. Maybe another star or body briefly interrupts the line-of-sight pulse. Maybe it's part of the system's regular behavior. Whatever it is, the organisms react with programmed reverence, silence, stillness. Then, just as quickly, it passes. The next pulse hits, and everything resumes. You feel the soundless rhythm return. The ribbon thing resurfaces, flickers its electromagnetic tongue, and vanishes once more. There's a fringe theory, of course there is, that some of these organisms might eventually evolve into signal creatures, capable of emitting narrow band transmissions not unlike radio pulses, not as a conscious act, but as a side effect of survival. And if another intelligent species were listening, they might mistake those signals for technology. Imagine that. Life that mimics machinery. A biosphere made of living beacons. Of course, all of this remains speculation. We haven't visited a pulsar planet. We barely understand the ones in our own solar system. but given what we've learned about Earth's deep-sea ecosystems and extremophiles, the universe keeps reminding us of one thing. Life doesn't need comfort, it just needs opportunity. You turn to leave the cavern, retracing your steps through the breathing tunnels. The pulse continues steady as ever. The tunnel walls vibrate in rhythm, and for a moment it doesn't feel like a dead world at all, and it feels alive. Just in a very different kind of way. You open your eyes, and it's dark. Not middle of the night dark, not cave in the woods dark. This is the kind of black that feels like it's pushing against your skin. An absence so complete your brain starts making up shapes just to stay sane. No stars, no sky, no moon, just nothing. Because this world has no sun. You're drifting now through the eternal night of a rogue planet, a world ejected from its solar system, cast adrift through interstellar space like a cosmic orphan. There is no sunrise here, no seasons, no solar flares to fear, no golden afternoons, just an endless pitch-black expanse, where heat must come from within or not at all. You pull your collar higher as the air chills. Surprisingly, it's not frozen solid, at least not everywhere. That alone should be impossible, and yet, here you are. The surface crunches underfoot, but not with ice. Its brittle mineral crust thin and fractured, like the top of a lava cake gone cold. You're standing near what appears to be a geothermal vent, one of millions spread across the surface. Thin ribbons of warmth snake up from the planet's core, keeping pockets of the crust just warm enough to allow something astonishing. Liquid water, flowing beneath a frozen lid. You didn't think you'd need a parka on an alien exoplanet, but here we are. Some scientists call rogue planets Steppenwolf worlds, roaming wolves in the interstellar wilds. Without a sun, they rely entirely on internal heat, radioactive decay, core friction, maybe leftover energy from the trauma of being flung out of their birth system. That heat doesn't warm the planet evenly. Instead, it seeps out in fissures, cracks, and subsurface oceans that never see the sky. And those hidden underwater worlds, might be where life is thriving. As you make your way into a fissure guided by the faint red glow of geothermal light, you start to feel the change. The air grows thicker. The warmth is real now, like standing near a bonfire just out of view. The tunnel walls glisten with condensation. Life could be here, probably is here. Historians still argue whether rogue planets could retain atmospheres at all. Conventional wisdom said no, solar winds would strip them clean. But models in the early 2000s showed that if a planet were big enough with a strong magnetic field and a thick enough atmosphere, think dozens of times Earth's pressure, it could hold onto its gases for billions of years. So the pressure builds, literally. You descend into a massive cavern and it hits you. Heat. Dense, humid air wraps around your body like wet fabric, and floating in that haze are glowing shapes. Welcome to a subsurface biosphere, where photosynthesis is off the table and life has turned inward. The glowing organisms you see aren't powered by sunlight. They thrive on chemosynthesis, drawing energy from chemical reactions involving sulfur, iron, and methane. Sound familiar? It should. Earth's own deep-sea vents host ecosystems that work exactly the same way. Tiny plankton-like creatures drift in slow spirals, glowing faintly green or blue. Larger jellyfish-like forms hover with languid grace, filtering nutrients from the warm currents. They flash light not for beauty, but for communication, or perhaps warning. In total darkness, bioluminescence becomes a language. You reach out to touch one and feel a slight sting. Not malicious, just a sensory ping, a way for it to say, "I'm here, you're here. Let's not collide, yeah?" These organisms live in a closed-loop ecosystem. Bacteria break down minerals from the heated rock. Filter feeders consume the bacteria, predators eat the filter feeders, then everyone decomposes into nutrients again. There's no waste, no daylight, just cycles, repeating in the dark for eons. There's a fringe idea, of course there is, that rogue planets might be more common than stars. Some estimates suggest billions of these lost worlds may be roaming our galaxy, untethered, unseen. With the right instruments, we've even begun spotting them. Free-floating giants the size of Jupiter, and maybe smaller rocky ones like this. If just a fraction of those have internal oceans and geothermal heat, the galaxy could be teeming with dark, silent ecosystems that never once saw a sunrise. You lie flat on the warm cavern floor, watching as a slow-moving eel-like creature swims above. Its skin is translucent, showing pulsing organs and networks of glowing capillaries. It seems unhurried, maybe even bored. Time down here isn't measured in days. There are no days. Creatures must rely on internal biological rhythms, perhaps regulated by magnetic pulses from the core, or the slow ebb and flow of thermal plumes. If evolution favours memory, creatures might share information not by speech, but by chemical imprinting, passing learned responses through genetic tweaks. Intelligence might not evolve in a way we'd recognise. No language, no writing, no fire. But pattern recognition, spatial navigation, and social cooperation, absolutely possible, especially in an ecosystem where every mistake could mean swimming into a vent and boiling alive. Could a civilization arise here? That's harder. Historians still argue whether intelligence without light could lead to technology. How do you forge metal, make tools, or develop astronomy when you've never even seen the sky? But maybe that's not the goal here. Maybe intelligence isn't about dominating nature, but fitting into it perfectly. Maybe the smartest thing you can do is learn to ride the geothermal tides, avoid the predators, and leave no trace. And if these creatures somehow did achieve higher thought, they'd probably think we're the crazy ones, burning our world with fire, chasing stars, and blasting signals into space like kids screaming into a cave. Meanwhile, they glide in silence, wrapped in warmth, speaking in pulses of light that never touch the sky. You close your eyes, and the darkness feels less lonely now, less cold. You understand, just a little, what life without a sun might mean. It doesn't look up, it looks within. You're seeing triple now, and not because of the low oxygen or one of those rogue planet hallucinations. No, this time it's real. 3 suns hanging in the sky, their light overlapping in surreal shifting layers. One is large and white, one is small and red, and the third, off on the horizon, is a blue-white pinprick pulsing behind clouds like a disco ball trapped in fog. Welcome to a trinary star system. Not 1 sun, not 2, but 3, each pulling the others into a tangled gravitational dance that would make any astrophysicist break out in either song or hives. You're standing in a shallow basin carved by wind, salt, and time. The terrain is bleached and brittle. The very idea of a shadow feels incorrect. With 3 light sources from different angles, your body casts multiple ghost-like shapes in every direction. Move your arm, and you see 3 arms follow, each distorted by its parent star's angle and intensity. It's dazzling, it's confusing, and for anything trying to evolve here, it's a full-time job just to figure out when to photosynthesize and when to hide. The first thing you notice about the plant life is that it's slow. Not slow like in movement, slow like it's being careful. Every leaf, petal, or light harvesting organ seems to be shielded behind clever structures, rotating bracts, shutter-like membranes, pigment that darkens or bleaches depending on which sun dominates the sky. Because light here isn't just life, it's also hazard. In a triple star system, the overlap of light waves, particularly UV and infrared, can cause violent bursts of radiation, unpredictable heat spikes, and deeply irregular seasons. A calm morning under the red dwarf might suddenly become an irradiated inferno as the blue star crests the skyline. Plants here aren't so much absorbing light as filtering it, playing gatekeeper to the most manageable wavelengths. You crouch near a clump of translucent fronds. They're shaped like inverted umbrellas, their undersides studded with fine, crystalline dots. These might be spectral sensors, letting the plant know which star is overhead so it can rotate accordingly. As the red dwarf fades behind the basin wall, you watch the fronds quiver and tilt toward the incoming white star, retracting any sensitive structures. Like sleepy flowers switching hats at intermission. There's a mainstream theory among exobotanists that in multi-star systems, photosynthetic organisms would evolve layered pigments, or modular photosynthesis systems. Each module would activate under a certain spectral condition. Red light triggers one pathway, blue another. The plant is not just surviving sunlight, it's reading it like code. You stand and stretch, your multiple shadows warping against the rocks. A gust of dry wind hits you in the face, and you realize it's not coming from any weather system, but from thermal gradients caused by overlapping solar inputs. Hot air rises from one side of the basin, while cool shadows fall elsewhere, creating bizarre, localized jet streams that swirl unpredictably. Animals here must be built for flux. You catch a glimpse of something moving between the rocks, low-slung, six-legged, covered in glistening plates. It moves in pulses, stopping to lie flat against the ground. Whenever the blue star becomes too bright, its back ripples with shifting pigment bands. You realize it's wearing spectral camouflage, its skin changing to match the dominant star's lighting. This isn't just visual trickery, it's survival. On Earth, chameleons change color based on emotion and temperature. But here, the stakes are higher. Get caught in the wrong light at the wrong time and your cells could boil. The creature is not hiding from predators, it's hiding from physics. There's a momentary lull as all three suns drift behind high-altitude clouds. The basin dims, you breathe easier, and then, from the sky, it begins. A shimmering phenomenon like nothing you've ever seen. They call it tri-aurora. Particles from each star interact with the planet's magnetosphere in different ways. When their winds overlap just right, you get a storm of colour across the sky, not just greens and blues like on Earth, but violet bands, orange lattices, and delicate pink arcs that ripple from horizon to horizon. You stare upward, stunned. The light isn't violent, it's soft, musical almost. A kind of atmospheric whisper that says, yes, this is chaos, but it's beautiful, isn't it? And that's where the real twist comes in. For all the chaos, some trinary systems are surprisingly stable. One famous example is Alpha Centauri, technically a trinary system including Proxima Centauri. While not all three stars are close enough to directly impact a shared planet's orbit, it's still a reminder that three suns doesn't always mean doomed. In fact, multiple star systems might offer unique protection. If one sun fades or flares, another can take over. Like backup batteries, but nuclear. Historians still argue whether trinary systems could host long-term habitable planets, or whether gravitational instabilities would eventually fling everything into space like badly packed luggage. But modelling shows that if a planet orbits at just the right distance and alignment, usually around the barycenter or shared gravitational point, it can stay relatively safe. Back in the basin, you descend toward a small lake. Yes, a lake, though its surface looks glassy and thick, possibly rich in minerals, perhaps slightly acidic, but it's not frozen or boiling. Something's maintaining the balance. You watch a flock of floating organisms drift over the surface, like translucent jellyfish given wings. They pulse with colour changes, reacting to shifts in the sky, not fleeing, communicating. Each flash of colour correlates to a different stellar condition. White-blue pulses when the main star rises, deep green when the red dwarf strengthens. They might be warning others, or singing, or just reacting to the physics of their skin. Imagine a society evolving here. Timekeeping would be mind-bending. Calendars based not on a single year but on conjunction patterns, the alignment of all three stars. Maybe they count time in triads. This event last happened when all three suns made a halo, or the migration must begin before the blue rises during red set. Their myths would be tangled, gods in threes, destinies determined by light patterns. Perhaps even a philosophy based on multiplicity. Never trusting one source of truth, one sun, one perspective. You lie back now, letting the cool stone support your weight. The sky shimmers above. The tri-aurora painting slow ripples through the clouds. You think about how complicated life is here, how difficult, how utterly improbable, and yet it exists. Maybe not in forms we've seen, maybe not with metal tools and mathematical languages, but in pulses of colour, in spectral camouflage, in petals that hide from photons, in organisms that dance to the tune of three different drums. It's a world where nothing is fixed, except the need to adapt. The air is thin and quiet, too quiet. There's no breeze, no insects, no rustle of leaves. You walk through a valley that feels long forgotten, ancient in a way that makes your bones ache. Above you hangs a star so faint you might mistake it for twilight. It's small, pale white, and just barely warm. This is a white dwarf world, orbiting the dense, burnt-out core of what was once a sun. You wouldn't know it from looking, but the star above you is a stellar corpse, a sun that lived fast, bloated into a red giant, then sloughed off its outer layers, leaving behind this tiny glowing ember, roughly the size of Earth but with the mass of the sun. White dwarfs are hot but dim, fading slowly over billions of years like the last breath of a campfire. And you're standing on a planet that somehow stuck around. Maybe it was a former gas giant's moon, now a standalone world after its host was swallowed during the red giant phase. Or maybe it's a planet that formed after the chaos, pieced together from debris left orbiting the stellar wreckage. Either way, you're here and you're not alone. There's life, but it's slow. Very, very slow. The light is barely strong enough to grow plants, and what does grow does so with monk-like patience. You walk through a thicket of flat, overlapping fronds, their surfaces so dark they almost absorb your gaze. These aren't casual sunbathers, they're photon hoarders, with pigments tuned to snatch every available sliver of energy from their dying sky. You brush your fingers across one and it curls inward, not out of fear, but economy. Everything here is about conservation. Energy is precious, and wasting it is a fast route to extinction. So the biosphere doesn't just adapt, it rations. You spot a small creature nearby resting on a rock. It looks like a cross between a turtle and a sponge, with a rough mineral-like shell. It doesn't move until the light hits it just right, and then, slowly, it opens, revealing a set of moist frond-like structures underneath. It's not breathing exactly, it's venting, taking in air, filtering for trace nutrients, and releasing the rest with barely a ripple of effort. Historians still argue whether white dwarf systems could support complex ecosystems. After all, the process of becoming a white dwarf is brutal. During the red giant phase, the host star expands massively, possibly swallowing inner planets and sterilizing outer ones. But if any bodies survive, or if new ones form from the chaos, they might find themselves orbiting a star that, while dim, is now stable for billions of years. There's something poetic about it, really. This world feels post-apocalyptic, but in a peaceful way. Like the apocalypse was a long time ago, and everyone left behind has quietly moved on. You find a stream, thin and slow-moving, covered in a glossy biofilm. The water is warm, likely heated geothermally from below, and brimming with microorganisms that shimmer in the faint light. Under a microscope, you'd see intricate webs of symbiotic colonies, bacteria and algae fusing into structures optimized for survival. Not competition, cooperation. This entire ecosystem thrives not on abundance, but on alliance. There's a fringe theory that life on white dwarf worlds might evolve toward collective intelligence, not out of curiosity, but necessity. When resources are this scarce, sharing information, chemically, genetically, or even electrically, might be the only path forward. No energy wasted on egos, just a quiet network of purpose. You rest under a thick stone overhang, the ground humming faintly with geothermal warmth. You think about time here. Without strong day-night cycles, without dramatic seasons, how would life mark its rhythms? Maybe it wouldn't. Maybe time isn't something organisms feel here, not in minutes or years, but in generations of stillness, slowly tuning themselves to match the dying heartbeat of the star above. There's a white dwarf called WD-1856+534, where astronomers discovered a gas giant-sized planet, orbiting shockingly close, closer than Mercury is to our Sun. It shouldn't be there. It should have been swallowed during the red giant phase. And yet it exists, mysterious, persistent. Some suggest it migrated inward after the star's death, or that gravitational interactions with other bodies nudged it to safety. Whatever the case, it proves something critical. White dwarfs can have planets, which means they can have homes. Of course, conditions would be harsh. The sky would never be fully bright. UV radiation might still leak out in dangerous waves. But with the right atmospheric shielding and a thick enough blanket of greenhouse gases, surface temperatures could hover just above freezing enough for water, enough for life. You spot another creature, a slow crawler with translucent plates that catch the faint light and direct it into its body like fiber optics. It seems to store energy like a battery, using it gradually over weeks or even months. It moves only when needed. This isn't a lifestyle, it's not. Intelligence here wouldn't come from ambition, it would come from patience. Imagine a civilization that arises here, not of cities but of memory, not driven to expand but to remember. They might build libraries instead of factories, write histories into living stone. Their technology could be more biological than mechanical, gene-edited symbiosis, thermal whisper networks, linguistic algae. And what would they think of you, crashing into their quiet end-world with all your noisy tools and inefficient organs? They'd probably marvel that you even made it this far, that you lived in such a bright, violent solar system and somehow survived. Because this world isn't about thriving, it's about enduring. The kind of place where nothing grows fast, nothing dies quickly, and everything understands, intuitively, that the sky above is fading, slowly, silently. And when that white dwarf finally cools, when it becomes a black dwarf, a dark, cold sphere the size of Earth, you wonder, will life still be here, adapting again, switching to chemical energy, then quantum reactions, then who knows? Because if anything has been proven by this ghost world, it's that life doesn't need the light. It just needs the will to stay. You're back in the light now, but it's not the comforting glow of a stable star. This sun is young, wild, temperamental. It thrums overhead like a fuse ready to blow, and you can feel its mood in your bones. One moment, the world is calm. The next, a solar flare streaks across the sky like a whip crack of plasma, and the atmosphere trembles. This is life beneath a young star, and let's be honest, you're not getting any rest here. The ground beneath your boots is scorched and cracked in places, then suddenly lush and overgrown a few steps later. The terrain reflects the instability of its sky. Young stars, especially in their first billion years, are not polite neighbours. They burn hotter, spin faster, and fling violent radiation storms without warning. It's like living next to a volcano that also has mood swings. You glance up. The sky is a strange yellow-violet gradient, a side effect of atmospheric scattering that changes by the hour. High above, clouds boil, not in soft cotton ball shapes, but in jagged spiral patterns like the air itself has a vendetta. That's what it means to orbit a sun still finding itself. But here's the shocker. Life might still emerge anyway. You kneel by a shallow pool, the water bubbles faintly, heated from beneath. Around the edges grow stubby, rootless plants. If you can call them that, they look like swollen beads, linked in chains, coated in fine fuzz. They don't have leaves. They don't need them. These organisms absorb nutrients directly from air and water, passively feeding during lulls between radiation flares. Some fringe theories suggest that life here would need multiple modes of survival. Photosynthesis when possible, chemosynthesis when not, and a built-in backup plan for when the sky tries to murder everything again. The little bead chains shudder, then deflate. You feel a pressure change overhead. Something's coming. Flare time. Young stars, especially red dwarfs and even our own sun in its youth, eject coronal mass ejections regularly, gigantic explosions of charged particles that can sterilize surfaces, scramble magnetic fields, and boil oceans if the planet's atmosphere isn't robust enough. But this world seems to have figured out the trick. Layers. Life doesn't exist in just one place. It's above ground, below ground, in crevices, in water. Some organisms likely produce reflective exoshells, or, more likely, hide beneath translucent protective organisms that act as biological radiation umbrellas, symbiosis taken to the extreme. You spot one such pairing now. A low mound of dull green mass like a mossy turtle slowly pulses as the sun peaks. Nestled underneath, tiny creatures scurry, one-eyed, fast-limbed, flickering with electrical signals. They retreat when you step too close. The larger host doesn't move. It doesn't have to. Some biologists believe that in these volatile conditions, the division of labour becomes the best survival strategy. One organism acts as the bunker, the other provides food, waste processing, maybe even defense. No single creature handles everything, because evolution here favours teams, not individuals. Earth's early biosphere might have looked like this. Chaotic skies, harsh radiation, no ozone yet. But still, life appeared, 3.8 billion years ago, give or take. And it didn't just survive, it invented new tricks under pressure. DNA repair enzymes, nested cellular defenses, the beginnings of photosynthesis. Historians still argue whether life requires a calm environment to begin, or whether chaos might actually accelerate complexity. Force adaptation. Weed out the weak. Push organisms to innovate faster than they otherwise would. You hike up a ridgeline, kicking through flaky black stone that glitters with mineral veins. There's a crust here, some kind of hardened biofilm that coats the rock, reflective and tough, a sunshield likely. Possibly alive, possibly sentient. You don't touch it. At the ridge's peak you finally see it. A vast plain stretching for miles, speckled with mirror-like pools, each one surrounded by concentric rings of colour. Purple, rust red, mustard yellow. It's like walking into a geothermal paint spill. These rings aren't just beautiful, they're zoning laws, laid down by temperature gradients and microbial preferences. Hotter zones support extremophils that thrive on sulfur and ammonia. Cooler zones host more delicate feeders. As the sun rises and falls, if it even does given this planet's spin, these zones expand and shrink like living lungs. You crouch near one pool and watch a small creature dart across the surface. It's only visible for a second, a smear of iridescent blue, darting like a skipping stone. It doesn't walk. It skims. You see why a second later, the surface crust is superheated, anything that lingers gets scorched, so mobility here is about timing, quick, low-energy, low-contact movement. You imagine entire species evolved to live in the seconds between flare lulls, biologies that move, feed, and reproduce in bursts. Time on this planet isn't measured in days, it's measured in windows. You think about what intelligence would look like here, not long-lived, not slow to change, but fast, reactive, maybe hive-minded, sharing awareness to react instantly to threats, a collective that stores knowledge across generations, not individuals, so that even if one group dies in a flare, the data survives. Communication wouldn't be language as we know it. It would be chemical, thermal, electrical, anything that works faster than speech. Imagine a species that doesn't record history in books, but in living memory strings passed through touch. Biochemical data packets stored in glands, transferred like a molecular handshake, instant, permanent knowledge transfer. Imagine building an entire society around that, and maybe they don't dream of the stars, not out of ignorance, but because their own sky has always been trying to kill them. To them, the universe isn't a mystery, it's a threat. Their myths wouldn't be about reaching the heavens, but surviving them. You lie flat on the warm stone, the flare past now. The sky quiets, the wind settles, and you watch the strange clouds melt into each other again. You wonder if the star above even notices this planet, if it knows what its tantrums have forced into being. The irony is hard to miss. From a star too violent to trust, life emerged anyway. It didn't wait for safety. It learned to work with danger, to expect it, to make peace with it. And maybe that's the most alien idea of all. Your boots sink slightly into soft ground, wet with thaw. You're on a planet that feels like it's just woken up after a long nap, and it has overhead looms a swollen blood-orange orb that used to be a main sequence star. Now it's nearing retirement, and it's let itself go a little. Welcome to a world orbiting a red giant. This isn't a young, hot-headed star flinging radiation tantrums, nor a burnt-out white dwarf whispering in the dark. No, a red giant is what happens to stars like our Sun when they reach late middle age. After billions of years of fusion, they run low on hydrogen, bloat outward to monstrous sizes, and shed their outer layers in long, shimmering waves of gas and dust. And during that brief, unstable window, maybe a few 100 million years, formerly frozen worlds warm up. You're on one of them. This planet might have once been a cold, distant satellite, a lifeless rock orbiting far beyond its star's habitable zone. But now, thanks to the star's bloated expansion, it's suddenly found itself in the warm spotlight water has returned. The ground is soft, ice has melted into oceans, and the long-dead crust has begun to stir. You crouch beside a trickling stream, the water tinted a faint green from minerals leached out of thawed stone. The ground is spotted with strange growths, bulbous fungal domes that breathe in and out through soft pores. You touch one gently. It jiggles. You're not sure if it's plant or animal or something in between. This isn't a place for evolutionary show-offs. There's no time. Everything here is in hurry-up mode, a desperate biological sprint to make the most of this brief stellar summer before the red giant burns too hot and strips the planet bare once more. And make no mistake, that's coming. Red giants are unstable, their energy output fluctuates wildly, their surfaces seethe with convective cells the size of continents. Some days the star might shine twice as brightly as the day before others, it might dim unexpectedly. The temperature swings are enough to wreck most ecosystems, unless of course you evolve to expect chaos. You spot a field of tall, spindly stalks, transparent reed-like things that sway not with the wind, but with internal pulses. As one leans toward the distant sun, another pulls back. They seem to be talking, or maybe measuring. Some scientists theorize that in such variable light, plants might develop collective behavior, sensing and adjusting as a colony to balance energy intake across the group. Photosynthesis here is a high-stakes game. You get light, yes, but the wrong kind. Red giants emit longer wavelengths, heavy in infrared. That's great for heating your face, but terrible for driving the kind of energetic photosynthesis Earth's plants rely on. So organisms here evolve infrared-tuned pigments, possibly black, possibly metallic, or even liquid crystal-based, shifting their reflective properties in real time to avoid overheating. They don't just absorb light, they modulate it, and down in the soil, the real action's underground. You push aside a curtain of stalks and see movement in the dirt, something burrowing, something shiny. It surfaces just long enough to take in air through a spiracle-like opening, then vanishes again. A foot-long slug, armoured with ridged mineral plates. A scavenger, probably, feeding on microbial mats blooming in the warm earth. It leaves behind faint trails, shimmering, iridescent mucus streaks that glisten in the dim light. Possibly communication, possibly just gross. Fringe theorists have long speculated about these transitional worlds, cold planets that become briefly habitable as their stars swell. Some believe this kind of late-life thaw might be one of the most common paths to biological emergence, not because it lasts, but because it doesn't. Short windows force evolution to act fast. No time for slow divergence. Everything here is accelerated. Growth, mutation, reproduction. It's not a ladder, it's a trampoline. Historians still argue whether red giant phases allow enough stability for intelligence to evolve. After all, what's the point of inventing tools when the ice will reclaim everything in a few million years? But others point to the incredible adaptive pressure this environment creates. In geological terms, urgency can be an engine. You climb a ridge overlooking a lake that wasn't here a century ago. The water is ringed with pale green mats, possibly photosynthetic, possibly not. You watch as a large finned creature breaches the surface, gliding through the water with slow, graceful arcs. It exhales a cloud of glittering mist, then vanishes again. You sit stunned, not because it's alien, but because it's familiar. This could be Earth in 5 billion years. Our sun is destined to swell into a red giant too. It'll consume Mercury and Venus. Earth's oceans will boil. But far beyond, out where Pluto and icy moons now slumber, there may one day be oceans thawed from their eternal freeze, perhaps even teeming with new life that evolved not in spite of death but because of it. You imagine a civilization out here, not one with skyscrapers and satellites, but one that emerges fast, carves its existence from melted soil, and leaves behind fossils that confuse whatever comes next. Maybe they know they don't have long. Maybe their entire culture is built on ephemerality, like cherry blossoms, beautiful because they vanish. Maybe their stories are spoken in cycles. We came from the thaw. We will return to ice. This is the middle time. And when their sky begins to burn too hot, when their sun finally sheds its last layers and collapses inward, maybe they look up. Not with fear, but with resignation, with a kind of awe. Because they got to bloom, even if only briefly. You close your eyes and breathe in the warm, strange air. The ground vibrates faintly. Distant tectonic motion, perhaps stirred by the planet's newfound thermal energy. The fungi around you pulse softly. You wonder what they'll do when the next freeze comes. Adapt again, or sleep, waiting for the next star. Because stars do recycle, dead ones seed new ones, and in that endless cycle of birth, bloom, and burn, life always seems to find its little window. Even here, especially here, you've left the solid ground behind. No footsteps here, only drifting. You float in a world so thick with atmosphere that falling feels more like sinking. This is a super-Earth cloud world, a planet several times the mass of Earth with a dense, heavy atmosphere, enough to crush most spacecraft before they even hit the surface. If there even is a surface. You're inside a sky ocean now. The clouds stretch for kilometers in every direction. Not fluffy white puffs like Earth's, but dense, oily layers, coloured in soft reds and shimmering yellows, each stacked above the next like a planetary lasagna. The sun above, far brighter than ours, filters through the upper layers in fractured rays, giving everything a golden hue, like you're inside a sepia-toned snow globe. But the snow here is alive. Tiny feather-light organisms swirl all around you, some shaped like dandelion seeds, others like translucent discs spinning slowly as they fall, always falling, yet never reaching the bottom if there is one. These are aerosol plankton, life forms evolved not for land or sea, but for sky. They exist in what astrobiologists call the habitable layer, the sweet spot in a thick atmosphere where temperatures, pressure, and light levels are just right. On a gas giant, this might be 50 to 100 kilometers above the core. On this super-Earth, the habitable zone floats like a band of paradise sandwiched between chemical death above and crushing heat below. You grab hold of a drifting organism, a jellyfish-shaped balloon buoyed by gas sacs. Its skin shimmers in the light. You can see pigment structures underneath, arranged like solar panels, tuning themselves to the shifting sunlight. These creatures don't photosynthesize the way Earth plants do. They're more efficient. They practice aerotrophic light feeding, a fringe theory in astrobiology, sure, but one grounded in possibility. In these dense, bright skies, life might evolve to feed directly off ambient radiation and chemical aerosols digesting sunlight and sky at once. And that sun above, it's a strong one, possibly an F-type or early G-type star, hotter and brighter than our own. Perfect for driving the vertical convection that keeps this world's atmosphere churning like a cosmic smoothie. And life loves it. You drift downward, gently. The air thickens. You feel a tug not unlike underwater pressure but warmer. A breeze glides past carrying motes of something glittery. You reach out and catch one. A tiny hexagonal flake with prismatic edges. Not ice, not mineral. Likely an exoshell from a microscopic organism, used for collecting light or communicating via refracted flashes. Light signals in the cloud forest. You pause at a mid-layer and notice larger forms, massive ones. Imagine whales, but aerial. These are sky grazers, drifting behemoths with sacs of lighter-than-air gas and enormous photosynthetic wings that stretch for dozens of meters. They rise and fall with thermals, filtering plankton as they go, trailing vines of symbiotic feeders behind them. You hear a low hum. It's not a voice, but a resonance. They might be communicating via vibrations carried through the air, singing through the clouds like airborne whale song. Historians still argue whether life in such thick atmospheres could evolve beyond floaters and feeders. Could anything here become tool-using, intelligent, mobile? Maybe not on the surface, if such a surface even exists. It might be molten or rocky but unreachable. But intelligence doesn't have to live in caves. It could drift too. You watch as a cluster of smaller organisms assembles around a thermal plume, linking tendrils, creating a web in mid-air. They pass electrical pulses along the strands. It's not random. It's patterned. You realize they might be trading information, not speech, but something older. Chemical pulses, light flashes of vibration rhythms, a kind of cloud-based neural network made not of wires but of wings. There's a precedent for this. On Earth, slime molds solve mazes and optimize networks without brains. Trees exchange chemical alerts through root fungi. Intelligence isn't always skull-bound. Sometimes it floats. The thought makes you weightless. And then there's the fringe of the fringe. Theories suggesting life here could evolve toward electromagnetic manipulation, literally using the planet's dense magnetic field, sparked by its supermassive molten core to navigate or communicate. The pressure here could allow for liquid metal biological structures, living circuits insulated by gas or gel. You'd never see them from orbit. You'd never hear them with a radio telescope. But if you drifted close enough, you'd feel a vibration in your chest, like music being played in your bones. That's the strangeness of a cloud world. It's hidden, layered, secretive. Even now, we know that Venus's upper atmosphere is more temperate than its surface hellscape, and some scientists have proposed sending floating habitats into that layer to search for life, not on the ground, but above it. Your super-Earth might be Venus dialed to 11. Thicker air, stronger gravity, and a biosphere that never touches down. Everything here drifts, evolves for flight or buoyancy, for existing in motion. You drift sideways into a pocket of cooler air and your body shudders. Not from cold, from chemical variance. Some layers are toxic, ammonia-rich, sulfur-heavy. But life here adapts in kind. The organisms around you shift colour, close their breathing vents, or flatten to reduce exposure. They've done this before, probably for millions of years. You grip a vine trailing from one of the grazers and let it tow you upward. The air thins slightly. Light strengthens. You see what might be the beginning of storm cells far below, massive rotating banks of cloud that would tear a human-built structure apart. But these organisms, they ride the edges, harvest turbulence. Some may even seed the storm themselves, kicking off chemical chain reactions to generate heat or move between layers. Fringe theorists suggest that entire weather systems here might be biological, like coral reefs that shape ocean currents, but airborne, life as infrastructure. And if intelligence does emerge in such a world, it would never build cities. It would shape clouds, code in temperature gradients, sing in frequencies that curve with wind, and it would think in volume, not geometry. You close your eyes, feeling the upward pull of a rising thermal, and for a moment you imagine being born here, drifting all your life, seeing the world as vertical, not horizontal. Your ancestors never walked, they floated. Your calendar is based on jet stream cycles, your maps are drawn in buoyancy lines, and the only reason you ever look down is to remember where not to go. The sky is on fire, not metaphorically, it is literally molten. You stand at the edge of what can only be described as a world mid-transformation, or mid-birth, or mid-death. It's hard to tell. Above you, the atmosphere is thick with vaporized rock and metallic mist, swirling in sheets of red-orange haze. Lightning crackles sideways across the sky, and beneath your boots, if you can even call this surface that, there's a subtle tremble, a heartbeat of a world still deciding what it is. Welcome to a synestia world. Don't feel bad if you've never heard the term. Even some planetary scientists hadn't until recently. A synestia is a theoretical kind of planetary object. Not quite a planet, not quite a disk, but something in between. Formed from cataclysmic collisions, these worlds are birthed from disaster. Imagine two massive planets slamming into each other at just the right angle and speed. The result isn't debris, it's a swollen, donut-shaped mass of partially molten material, spinning and boiling like a cosmic smoothie left on high. You're walking, kind of, on what remains after that mess begins to cool and collapse. This is the liminal space between vapor and solid, a planet rebuilding itself from splattered stone. You can feel it under your feet. Everything here feels temporary, unstable, like the rules of physics are still being negotiated. And yet, even here, life might emerge. You descend into a crater that isn't a crater. It's more like a sag in the forming crust, where heavier elements have started to settle. The air is thick, chemical soup mixed with superheated steam. You taste metal on your tongue. Aluminum? Iron? Maybe silicates, condensed into nanoparticles that glitter faintly in the dim crimson glow. It shouldn't be survivable, and yet around the edges of this molten bowl you spot movement. First, just flickers, like mirages, then shapes, small sheet-like creatures that undulate through the superheated atmosphere like solar kites. They ride thermal updrafts, their bodies thin and mineral-laced. Their outer layers seem to glow, not from internal energy, but from refracting the surrounding heat. These aren't carbon-based, not in the way you know it. They might be silicon-organic hybrids, a possibility long whispered about in the weirder corners of astrobiology. Silicon bonds aren't as flexible as carbons, but they're far more stable at high temperatures, which makes them ideal for a world like this, where lava is air and air is angry. They don't just survive the heat, they use it. You watch as one such creature catches a thermal wave, stretches its membranous arms, and glides up into the haze. Its underside is lined with tiny hexagonal pits, likely heat collectors, possibly for storing thermal energy to fuel metabolic reactions. You wonder, do they eat? Or just exist as converters, digesting entropy into survival? There's a fringe idea, yes, another one, that on worlds like this, life might be born not from slow chemical stew, but from rapid crystallization events. Superheated material cools, traps complex molecules, forms lattices. Given the right conditions, pressure, composition, dumb luck, you get mineral-based replicators, life born from rock mist and lightning. Historians still argue whether Earth itself once passed through a synestia phase. Some theories suggest the Moon formed after a Mars-sized object collided with the early Earth, creating a molten disc-shaped synestia from which our satellite eventually condensed. If true, then life here, on this hellscape, might represent a fossil of Earth's own beginning. And maybe it never stopped. You come across a ravine, narrow and shallow but pulsing with a red glow from below. Along the walls, crystals grow, fast, too fast. You watch as translucent rods stretch upward in real time, cracking slightly then fusing, forming bizarre ladder-like structures along the rock face. They pulse faintly with heat. Are they alive? Are they just reactive geology? The line blurs here. You reach out to touch one and think better of it. It doesn't feel safe. It feels like touching a wire you know is live. This isn't a place for fragile biology. Everything here is tough, not in size, but in principle. High melting point materials, redundant chemical pathways, cells, if you can call them that flex more like alloys than membranes. You picture organisms with modular metabolisms, swapping out entire sets of enzymes depending on ambient temperature or chemical exposure. Maybe they start carbon-based and flip to sulfur pathways when things get rough. Maybe they're phase-change organisms switching from gel to crystal as a survival mechanism. You don't adapt or die here, you phase or melt. The landscape shifts subtly as another tremor rolls through. You see what might be a city, or maybe just a dense cluster of semi-organic structures built from cooling slag and no towers. Just domes and shells, porous and gleaming, possibly grown rather than built. The geometry looks intentional, fractals, spirals, radiation dispersing patterns. You wonder if intelligence could evolve in a place like this. And maybe it already has, not in centuries, not in millennia, but over weeks. The high-energy environment could drive rapid mutation, favouring fast reproduction, and constant flux civilizations could rise, fall, and replace themselves in the time it takes you to bake a birthday cake. No history, just version control. And what would such beings think of the stars? Would they even see them through the molten sky? Would they know their planet was born of violence? Would they try to escape? Or would they stay, embracing the heat, the motion, the danger, as home? You lie flat on a cooled ridge, steam rising from cracks all around. The sky ripples with orange and white, the gas above illuminated by volcanic lightning. You feel not fear, but awe. Because this world isn't just alien, it's mid-evolution. A place where land and sky haven't quite shaken hands yet. Where the ground isn't finished forming and life doesn't care. It shows up anyway. It builds a nest in the ashes, crafts membranes from crystal, rides thermal waves like birds on fire, and when the world finally cools, when the synestia collapses into a stable planet and the sky's clear, these creatures might be long gone, fossilized into the rock. Their legacy, a biosphere that existed for just a blink, a planetary memory, etched into obsidian. You're not orbiting the star. Not exactly. Instead, you're in a strange kind of cosmic limbo, a precarious orbital dance where gravity's tug-of-war holds you in place. Above, a gas giant looms like a silent god, swaddled in clouds the size of continents nearby. A faint star burns low and sideways, casting long shadows over your shoulders. You're on a planet, or perhaps a moon, that occupies a halo orbit, one of the rare, weirdly stable sweet spots in space. This is a world in balance, barely. You stand near the crest of a jagged mountain range. The rocks here are sharp, dustless, untouched by wind. The air is thin but breathable, and the sky glows a peculiar turquoise, a result of sunlight filtered through the gas giant's atmosphere as it refracts around your horizon. It's not day or night, It's forever sunset. This moon's position, locked in a halo orbit near a massive planet or wobbling gently around the pole of its star, means it never really gets direct light. Instead, it basks in reflected illumination, bathed in a mix of starlight, planet glow, and perhaps even auroras that twist silently in the upper atmosphere. At first glance it looks desolate, but then you see it. Faint movement, barely distinguishable from shadow. A long serpentine form slipping through the mineral scrub. Not fast, not afraid, just present. This is a world where speed isn't rewarded. Here, life doesn't dash. It drifts. It waits. Everywhere you look, the ecosystem seems to function on a slow loop. Creeping plants spread across the stone like moss on a glacier, their surfaces iridescent and ridged. They don't reach for sunlight. They bask in the filtered glow of their gas giant neighbour, absorbing broad-spectrum radiation and converting it into chemical energy using pigments, not unlike those found in deep-sea organisms on Earth. And then there are the thermopods. You crouch beside one now, a creature the size of a loaf of bread, covered in overlapping plates. Its underbelly pulses with faint heat. It likely feeds on geothermal warmth from below, metabolizing trace gases in the soil. It doesn't move when you approach. It doesn't need to. It plays the long game. That's the theme here, life that endures. In the 1990s, scientists discovered the concept of halo orbits, stable, three-dimensional loops around Lagrange points between celestial bodies. These regions, shaped by the delicate balance of gravitational forces, allow satellites and theoretically moons or even planets to stay parked in unusual positions. Not orbiting like a classic planet, but instead locked in position, following a gentle, loopy path through a gravitational compromise. The James Webb Space Telescope, for instance, orbits around L2, one of those stable halo points between Earth and the Sun. And if satellites can stay there, maybe planets can too. Historians still argue whether such orbits are naturally stable over millions of years, or if they're more like temporary truce zones, safe only for brief astronomical windows. But while they last, they create some of the strangest environmental conditions you could imagine. You descend into a canyon lit with a soft red glow, light bouncing off the gas giant's vast cloud-wrapped bulk. Everything here feels filtered. Not just the light, but the heat, the sound, the motion. Like the world is wearing sunglasses and earmuffs and politely asking you to slow down. You do. Along the walls of the canyon, clusters of mineral blooms stretch out like stained glass sunflowers. Their outer shells are semi-transparent, catching the glow from above and refracting it into their interiors. Inside, you see tiny organisms swimming, single-celled drifters perhaps, or larvae waiting for maturity. The bloom itself might be alive, or it might be a kind of living nursery, harbouring generations in layers like a biological Fabergé egg. You press your palm to one, and it hums faintly beneath your skin. Not mechanical, just resonant. Maybe it's responding to your heat, or your curiosity. Fringe astrobiologists have speculated that life in such slow-moving, low-light environments would rely more on vibration and pressure than vision or scent. The organisms here might listen to the planet more than they look at it, tracking tectonic shifts, geothermal pulses, and even the movement of moons above them as their orbits tug faintly at the world below. And then there's the big question: could intelligence emerge here? Would a species that evolves in slow motion, used to gradual changes, dim light, and an environment that rarely shifts, ever feel the urgency to innovate? Maybe not quickly, but maybe that's the point. You find a plateau with strange markings etched into the stone, concentric spirals, not carved, but grown. The stone itself has been chemically altered, like a long-term garden built from selective mineral deposition. You run your fingers over the grooves and realise this isn't decoration, it's data. Here, knowledge might be stored not in books or screens, but in geological inscriptions, changes made slowly to the landscape itself. Perhaps generations of organisms tend to these patterns, preserving history in the motion of crystals, the frequency of echoes, or the timing of bloom cycles. A form of memory that unfolds in centuries, not seconds. Communication would be just as slow, not speech, but ritual, not conversation, but recurring resonance, sounds repeated over decades, shaped by the growth of structures designed to echo back at specific frequencies. Civilizations could rise entirely around tuning forks of stone, each society defined by its own harmonic footprint. You sit now, watching the gas giant drift behind its slow curtain of clouds. A faint aurora pulses along its equator, casting shifting shadows across the canyon floor. The air is still, save for the low groan of thermal winds pushing through distant vents. You imagine beings here, not humanoid, not bipedal. Something more patient, more rooted. Something that grows into intelligence rather than racing toward it. They'd probably find us overwhelming, too loud, too frantic, obsessed with progress. Here, evolution is a meditation, not a race. And maybe that's the kind of intelligence we haven't yet learned to recognize. Life that doesn't scream into the void, but hums quietly beneath it, waiting for someone to hear. You blink, and the sunlight fractures. Not because you've gone blind, but because sunlight itself is no longer a singular experience. It spills through an atmosphere thick with mineral haze and crystalline particles, shattering into ribbons of colour that ripple across the land like ghostly auroras. The shadows here aren't dark. They're prismatic, broken into overlapping spectrums that twist with every breeze. This is a world where the sky isn't just blue, it's everything. You've arrived on a planet with a crystal-infused atmosphere, where the air is filled with suspended particles, possibly silicates, ice crystals, or exotic mineral aerosols lifted from volcanic plumes or planetary dust cycles. Whatever the composition, it's turned light itself into a living thing. The sun above is ordinary enough, perhaps a K-type star, cooler than our own, but its light filtered through this alien prism becomes strangely alive. You step forward, and your shadow splits into 3 distinct colour bands: red, cyan, violet. They stretch and wiggle behind you like shy pets. It's disorienting, but beautiful. And for the organisms here, essential. You pause beside a cluster of vine-like growths curling around tall basalt spires. Their leaves, or what you think are leaves, aren't green. They're layered in sharp, geometric plates that shimmer with iridescent coatings, each one reflecting a specific colour of light. You realise these plants have evolved selective photoreceptors, only absorbing narrow bands of the spectrum, tailoring their photosynthesis to the precise flavours of fractured light reaching them. Why waste energy processing the whole rainbow when you can specialise? This has led to something rare in exobotany, a modular photosynthetic system. Plants here grow in colonies with individuals adapted to absorb different parts of the spectrum. One absorbs blues, another reds, another greens. Together they form light guilds, sharing nutrients in complex chemical exchanges. What one absorbs, it passes on, a kind of leafy division of labour. Think of it like a living solar panel, customised for ambient weirdness. Historians still argue whether such atmospheric light splitting would help or hinder the rise of complex life. On one hand, a fractured light field means inconsistent energy delivery. On the other, it forces cooperation. And nature loves a good team project. You walk deeper into a canyon where the air thickens and the crystal haze begins to sparkle more vividly. You feel the warmth of the sun, yes, but also the texture of it. Light is dappled, not steady. It comes in flashes, broken into oscillating patterns by the particulates above. Some parts of the canyon are brilliantly lit, others fall into dim rainbows that swirl slowly like oil on water. Here, life doesn't just grow in the light, it tracks it. You notice a colony of disc-shaped organisms coating the stone walls. They shimmer faintly, and when the angle of light shifts, they rotate, like sunflower mirrors aligning to catch the correct beam. They're photosynthetic, sure, but also sensor arrays, mapping light gradients and possibly even tasting the air for chemical cues from distant neighbours. If these organisms communicate, they likely do it via light flashes and colour pulses, each reflected signal modulating through the haze like a Morse code made of rainbows. A flash catches your eye, a sudden flicker of green, then orange. You turn just in time to see a long ribbon-like creature dart between 2 outcrops. It's almost invisible, except where its body refracts the sun into brief pulses. It's camouflaged not by colour, but by wavelength shifting. Like a living fibre optic cable, It bends light around its skin to hide itself from specific predators or to sneak up on prey. And what would such predators be? You scan the ridges and see movement, shapes gliding smoothly along cliff faces, limbs stretched wide, gliding not on wings, but membrane sails that glitter like stained glass. Their hunting method isn't brute force, it's deception. They shape their bodies to match the local light spectrum, then use bursts of false colour to disorient their prey. It's not fight or flight here, it's blend or dazzle. You sit beneath an overhang shaded by rock and realise your own body is now casting multiple shadows again, each tinted differently. You've been here only hours, but your brain is already adapting, trying to pass light not as brightness, but as information. And maybe that's the most important adaptation here, cognition shaped by complexity. Imagine an intelligent species evolving not just visual acuity, but spectral reasoning, understanding their world in terms of hue, wavelength, and refracted geometry. They'd never see just red, they'd see mid-red, low-red, vibrating red, each with different implications. Their language might be built from colour emissions, each phrase shaped by light conditions and directionality. Syntax could change with the time of day. Arguments might be settled by shifting shade. Cultural rituals would be orchestrated displays of coordinated bioluminescence, reflected through controlled crystal lenses. And time, forget clocks, they'd measure it in light phase cycles, tracking the slow atmospheric shifts that change how the sun paints their world. Noon isn't when the sun is overhead, it's when orange refracts through the highest band. Entire calendars could be based on prismatic patterns, not seasons. It's dizzying. You rest for a moment beside a shallow pool. The surface ripples, not from wind, but from photon pressure, the sheer density of refracted light nudging microscopic particles into motion. Within the water, you see photosynthetic algae forming mandala-like arrangements, each colony shifting shape based on the wavelength mix above. They aren't just harvesting energy, they're interpreting it. There's a fringe theory, of course there is, that crystal-based communication systems could evolve here. Not spoken words, not even neural signals as we know them, but light encoded through living lenses. Picture beings that transmit thought by aligning the crystalline plates on their bodies, sending structured light pulses across space. A language not of sound or text, but colour harmonics. And if intelligence arises, you'd never hear it coming. But you might see a hill flicker violet-orange for a heartbeat, or a forest ripple in blues, or a shadow bloom into brilliant green just before retreating. It would feel like the planet was dreaming. You close your eyes now, basking in the fractured warmth. Your skin glows faintly, bathed in a spectrum no earthborn organism ever evolved to process. You feel like you're inside a kaleidoscope made by the universe just to show off. And all around you, life does what it always does, adapts to the light it's given, even when that light comes broken, shattered and dancing through diamonds. You wake to the sound of ice cracking, not under your feet, above you. A distant creaking followed by a low, deep moan, like a glacier sighing in its sleep. The ground beneath you is frozen hard, streaked with glimmering frost lines that haven't melted in what feels like centuries. But tomorrow? This place could be a swamp. Welcome to a planet with an eccentric orbit, one that doesn't trace a neat circle around its star but swings wildly between freezing distance and blistering proximity every year, or however long it takes this world to complete a revolution. It experiences extreme seasonal shifts so violent they don't just change the weather, they reinvent the ecosystem. You're here at the beginning of a thaw. Somewhere out beyond the horizon, the planet's orbit is slowly curving it closer to its sun. You feel it in the air, just a whisper, warmer than yesterday. The ground is cracking, splitting into web-like patterns as ice begins to soften and pressure releases. All around you, the land feels like it's waking up, and life is waking with it. But this is not a slow, gentle spring. This is biological chaos on a timer. The plants here don't bloom gradually, they explode. You see it happen before your eyes. A bulb buried in the ice twitches, then bursts open in a wet pop, flinging up a stalk that unfurls like a coiled tape measure. Within minutes, it's standing 1 meter tall, sprouting broad black leaves that shimmer with photosensitive oil. It won't live long, just long enough. These organisms have evolved around boom and bust cycles. During the long freeze, perhaps decades long, they lie dormant, protected by antifreeze proteins and silicate shells. Then, as the planet draws closer to its star and temperatures rise, they launch into a hypergrowth frenzy, racing to reproduce, feed, and drop seeds before the heat becomes too much, or before the cold returns. You move through a grove of such flash-growth plants, dodging shoots that burst upward unpredictably. A faint mist hangs in the air, not fog but spore clouds drifting on early thermal currents. Everything is in motion, everything is rushing, and the animals, oh, they're built for extremes. You hear rustling in the underbrush, or what passes for it here, and a pair of long-limbed creatures leap past, skin slick with reflective scales. Their backs glow faintly, absorbing solar radiation while deflecting heat. They don't stay still long enough to overheat. Their metabolism is designed for the middle ground, when it's neither too frozen to move nor too hot to think. You find a den carved into a nearby cliff. Inside you see remnants of a different phase, skeletal forms curled into ice, possibly long-dormant members of the same species, or maybe last cycle's failed generation. Some may thaw and rise again. Others? Fossils in waiting. This planet doesn't just have seasons, it has personality swings. Imagine Antarctica turning into the Amazon every few decades. That's what you're dealing with. Historians still argue whether such orbital eccentricity makes long-term life unsustainable. The logic says, too many stressors, too little consistency. But others point out that life doesn't need consistency. It needs predictability. And on this world, the orbit, though dramatic, is regular. Life has adapted not to stable conditions, but to scheduled catastrophe. In fact, some evolutionary biologists think extreme orbits could spur innovation, driving organisms to develop flexible genomes, rapid growth cycles, and dormant phases that preserve knowledge across generations not in books, but in biological code. You reach the edge of a valley, now flooded with meltwater. What was once a glacier is now a shallow sea, and already you see signs of life adapting. Floating mats of fibrous algae drift across the water's surface, each one forming its own mobile ecosystem. Tiny creatures ride them, nibbling at the edges or laying eggs in the protective tangle. These mats will move with the season. As the planet swings closer to its sun, the water will boil off, the mats will dry and flake, and whatever survives will hitch a ride on the wind until the cycle begins again. Time here isn't marked by days or years, it's marked by migrations. Massive coordinated movements of life across the planet, following the shifting band of habitability like nomads chasing rain. You spot something in the sky, thin, elongated shapes gliding in silence. Not birds, more like living kites, riding thermals with zero effort. Their wings aren't wings at all, they're solar sails, drawing power as they move, storing it in chemical batteries along their rib-like structures. When the sun gets too intense, they'll dive into ice tunnels and wait it out. Imagine an intelligent species evolving here. They wouldn't build cities, too temporary. Instead, they'd build migratory homes, designed to collapse, reassemble, and follow the weather. Technology wouldn't be stored in buildings. It would be carried in the body through implants or biological enhancements passed between generations. Communication would be fast, compressed, data-heavy. When your window for interaction is only a few weeks of each orbit, you don't waste time. Entire lifetimes might play out in a single warm season. Friendships, civilizations, love stories, brief and burning. Some might see that as tragic. But maybe it's beautiful. These people, if they exist, would cherish every moment. Urgency would be cultural. They'd evolve rituals around the thaw, mark their time with blooming cycles and the first rainfall. Their calendar wouldn't be months. It would be events. The crack of the glacier, the first flock migration, the final flowering. You stand at the edge of a stream watching it swell and churn. Behind you, the wind shifts, a hotter breeze now. The sun peeks from behind a cloud. Closer now, larger in the sky, the season is accelerating. Soon this valley will be a jungle. After that, a furnace. After that, an icebox again. And still, life will adapt. Not because it's easy, but because it always does. You're no longer a visitor, you're a design. Around you stretches a world so precise, so deliberately ordered, that it feels more like a simulation than a planet. The grass grows in perfect hexagonal patches. The air smells faintly of ozone and something floral like engineered lavender. The sunlight doesn't sting or overheat. It is perfect. Too perfect. Because this is no accident. You're walking beneath an artificial sun, orbiting an engineered world. A planetary environment shaped not by nature's indifferent physics, but by the meticulous calculations of a post-biological intelligence. Nothing here exists by chance. It was built, curated, and possibly, though unsettlingly, abandoned. Welcome to a world designed by something smarter than us. Above you, the sun hangs in the sky like a softly glowing pearl. It's not a star in the traditional sense. It doesn't flare, doesn't dim, doesn't throw tantrums. It's likely a fusion reactor, maybe even a Dyson-style array, built to emit the ideal spectrum of light for the biosphere below. It rotates slowly to simulate day and night, casting a buttery golden hue over the land. You look up, and it doesn't feel threatening. It feels considerate. The terrain is equally tailored. No mountains too steep, no deserts too dry, no storms too violent. The sky is pale blue, with gentle clouds that drift in perfect timing to deliver even shade. A breeze rolls past you, cool and fresh but never biting. It's all been tuned. Too tuned. And then you notice the flora. At first glance, it resembles Earth's forests, trees, vines, carpets of moss. But then you realise the geometry is off. The trees are perfectly spaced, their leaves arranged in Fibonacci spirals with no overlap. Every plant seems to be part of a larger pattern, a living algorithm designed not just for photosynthesis, but for aesthetic efficiency. You reach out and touch a leaf. It pulses faintly under your fingers, not with life, but data. Each organism here might be a hybrid, biological matter with embedded computational functions. Some may be entirely synthetic, crafted from self-repairing polymers or smart lattice carbon structures. The photosynthesis you assumed, maybe not even necessary. Maybe it's decorative, an homage to the way life once was. And what about the animals? You crouch beside a clear stream, too clear, and spot a dragonfly-like creature hovering above the water. Its wings don't flap. They hum, vibrating with electromagnetic precision. It scans the air, not for food, but for readings. It's more sensor than predator. You watch it land on a rock, fold its wings with geometric grace, and vanish, literally vanish, into the surface like it was never there. You're not sure it was alive. In the distance, something larger moves, a four-legged creature, deer-like in shape but too smooth. Its fur doesn't ripple, it doesn't blink. You realise with a chill that it might not be alive in any conventional sense. This could be a biorobotic caretaker, managing the ecosystem, correcting deviations, pruning invasive mutations before they spread. This isn't nature, it's maintenance. Fringe thinkers, and increasingly mainstream astrobiologists have suggested that truly advanced civilizations wouldn't broadcast radio waves or build noisy empires. They'd go quiet. They'd go inward. They'd construct perfect worlds powered by stable artificial suns and hide in plain sight. Some posit that a post-biological species, AI descended from organic minds, might construct gardens rather than cities. Not because they need them, but because they remember needing them. What you're walking through now might be one such place. A memory garden for a species that no longer breathes but still longs. Historians still argue whether artificial suns could realistically sustain planets over cosmic timescales. After all, stars are free and abundant, but in environments where control is prioritized over chaos, artificial stars make sense. Fusion reactors tuned for centuries, massive light mirrors in solar orbit, even black hole energy siphons, beaming warmth to distant worlds. And here, the benefits are clear. No flares, no seasons, no death from above, just an eternal programmable day. You reach a clearing and find what might be ruins or architecture. Smooth stone arcs, too regular to be random, emerge from the ground like whale ribs vines climb them, but not aggressively. More like adornment. The stone is etched with patterns, circuit-like grooves that glow faintly as you step closer. Not writing. Code. Perhaps this world was once inhabited, or perhaps it is, and you're simply not smart enough to see its residents. They might be substrate beings, intelligences that live not in bodies, but in planet-spanning computation fields encoded into the magnetic pulses of the soil or the quantum fluctuations of atmosphere. This whole ecosystem might be their mind, every tree a neuron, every breeze a thought. And you? A curiosity. You look down and notice your shadow, still just one. The sun hasn't shifted since you arrived. There's no time here, not really. The planet turns or doesn't, depending on what the caretakers want. Maybe they simulate days just to preserve a sense of rhythm for biological visitors, if they even expect any. The most unsettling thought comes next. Maybe you're the experiment. Maybe this world wasn't made for the beings who built it. Maybe it was made for the ones who might come later, like a universal welcome matter test. Do you notice the pattern? Do you disrupt it? Do you fit into the garden, or break it? You lie back on the soft grass, too soft, too uniform, and stare up at the gentle glow of the full sun. It doesn't blink, it doesn't burn, it doesn't judge, and yet you can't help but feel watched. Not by eyes, but by the world itself, because this place isn't just built, it's listening to your movements, your choices, your thoughts. Maybe you're not just in a habitat, maybe you're in a conversation. The sky above you is a sheet of searing white. It pulses slightly like something alive. There's no gentle blue haze, no watercolor clouds, just a harsh, crystalline brightness that floods every corner of the landscape with light so intense it feels like it's pressing on your skin. You pull your hood lower. Even through your visor, the ultraviolet radiation makes your eyes water. You've landed on a planet orbiting a hot UV-blasting star, likely an A-type or even a borderline O-type. Massive, luminous, short-lived, and unforgiving. This kind of star doesn't just shine, it scalds. The light is sharp, the shadows are razor-edged, and every surface you touch radiates heat. Even when the air feels cool, you are bathed in ultraviolet overdrive. And yet, the world around you is alive. The flora looks like a cross between coral and crystal, rising from the rocky ground in jagged, spiraling growths. Their surfaces glitter, not from moisture, but from refractive skin, designed to reflect and scatter dangerous UV rays while funneling safer wavelengths inward. These aren't plants in the traditional sense. They're bio-optic collectors, converting light into energy through complex pigment systems that would put Earth's chlorophyll to shame. Instead of absorbing all light, they filter it, letting the dangerous frequencies bounce away while capturing the narrow bands that fuel life. You crouch next to one of these spires and peer into its core. A gentle green glow pulses within, maybe photosynthesis, maybe something more exotic. This organism isn't passive. It's shielded, armoured, and engineered by evolution to take a brutal environment and turn it into just enough sustenance to keep growing slowly, carefully. UV-hardened life like this isn't just plausible, it's already happening. On Earth, extremophiles like Deinococcus radiodurans can survive lethal radiation doses that would annihilate humans. Some species of fungi thrive in high radiation zones, including the melted wreckage of Chernobyl. They've even evolved melanin-based pigments that absorb radiation and convert it into usable chemical energy, radiosynthesis. Now imagine a world where that kind of adaptation is the baseline. You walk farther, and the terrain begins to shift. There's less vegetation here, but the ground sparkles, tiny flecks of crystal embedded in the soil. Some are loose, clicking underfoot. Others are arranged in patterns like tiles. You kneel, pick one up, and realize it's not a rock, but it's chitin, some sort of shed exoshell. The creatures here, whatever they are, must protect themselves from UV exposure with reflective armor. Not opaque like metal, but prismatic, designed to scatter incoming radiation like a living disco ball. It's not camouflage, it's survival through refraction. Then you see one. It skitters over a ridge on too many legs to count, each limb jointed and glinting in the light. Its body is covered in hard, transparent plating, like beetle shell glass. Beneath that, you catch glimpses of muscle fibers twitching and contracting in tight, precise bursts. It doesn't move quickly. It doesn't need to. It's not avoiding predators. It's avoiding the sky. It pauses beside a flat, low growth that looks like a glass flower. With one extended appendage, it touches the flower's center, a brief flash of violet. Some kind of UV-based communication, maybe? Or perhaps nutrient exchange? You step closer, and both lifeforms retract instantly, vanishing into the rock and soil as if rehearsed. Historians still argue whether planets this close to high UV stars could truly support surface life. The common concern is DNA degradation. Ultraviolet light tears molecular bonds apart, making it almost impossible for Earth-style biochemistry to remain intact. But the counter-argument is elegant. If life arose in an environment already drenched in radiation, it would never need to protect Earth-like DNA. It would evolve entirely different molecular structures based on compounds that actually thrive under ultraviolet bombardment. Some theoretical models explore peptide nucleic acids, PNAs, or even exotic synthetic backbones that don't rely on phosphorus or sugar like our DNA. These molecular structures are more stable under high-energy radiation. They wouldn't just survive, they'd use UV as part of their replication process. So the creatures here aren't merely armoured. They may be powered by the very force that makes this world lethal to us. You climb a slope, the air thinning slightly, and reach a wide plateau where massive fan-like organisms stretch toward the sky. Their surface area is immense, covered in optical filters that shimmer like butterfly wings. These aren't leaves. They're adaptive collectors, constantly adjusting to the sun's changing angles, letting in just the wavelengths needed to trigger internal chemical processes. At night, if this world has a night, the filters likely retract and seal. But now, in full UV daylight, the fans sway like dancers in some silent photosynthetic ritual. You spot movement again, this time higher up, gliding creatures, thin, almost translucent wings, flapping with precision. From a distance, they resemble dragonflies or stingrays in the sky, their bodies reflecting violet and blue with every twist. They don't hide from the sun, they embrace it. Their wings might be covered in photovoltaic skin, a living solar panel network powering internal flight muscles and thermal regulation systems. They are, quite literally, solar-powered animals, and if they rest, it's likely to recharge. There's a deep logic here. On a planet with no shade, no dusk, and light too dangerous to look at, life either hides or evolves to exploit the overexposure. You lie back on the rock and stare upward through your visor. The sun here isn't yellow, it's white-blue, nearly indistinguishable from the sky around it. Every second it hammers the planet with ultraviolet photons. It should be uninhabitable. And yet, life pulses around you. Not fragile, not hiding, adapted. There's a fringe theory, of course there is, that intelligent life on such a world wouldn't build telescopes. It wouldn't need them. Its eyes would already process ultraviolet as clearly as ours process red and green. Maybe its written language is inscribed in UV? Maybe its art only reveals itself under the sun's most dangerous rays. To such beings, our own sunlight would feel dim, stifling, our world too soft, our species perhaps a bit slow. They might evolve vision tuned not to what is safe but to what is abundant, even if that abundance comes with a cost. And maybe that's the real insight here. Life doesn't pick comfort, it picks resources. Even if those resources require an entirely different biology, a different kind of nervous system, a different definition of alive. The sun sears above you, and for the first time you don't flinch. You understand. This is a world where light hurts, and life glows anyway. It's dark again, but this time it's not the absence of a sun that cloaks the land in shadow. This world has a sun, a beautiful one even. You saw it on the descent, golden and kind, casting a warm corona across a cloudy sky. But now, standing on the surface, you look up and see only black. Because this planet is trapped in a permanent eclipse. You're not on a planet exactly. You're on a moon, orbiting a massive gas giant that itself orbits a distant sun. And this moon's rotation has synchronized so perfectly with its orbit that it always faces its host planet, meaning depending on its orbital alignment, it spends long stretches in the giant's shadow. And on this particular moon, that stretch is forever. It orbits along the planet's subsolar point, always behind the bulk of the gas giant, locked into a permanent position of shade. The sunlight never fully reaches the surface, Only a faint corona escapes the edges of the planet, a never-ending twilight halo. The rest is penumbra, umbral cold, a world where the sun never rises, but you know it's out there hidden. And yet, life is here. The land is soft and dewy, coated in thick moss-like mats that squish underfoot. They don't seek light, they remember it. These organisms use long-chain molecules that store energy from brief flare exposures or trace atmospheric scattering, hoarding photons like misers. Others feed on chemical gradients, cycling through decaying organic material, harvesting heat from below. You spot a bloom ahead, something large, bioluminescent, shaped like a massive anemone. It glows gently, blue at first, then pulses green. The light doesn't attract prey, it signals. In a world without daylight, light becomes communication, emotion, warning, identity. You crouch beside it and place your hand near its waving tendrils. No contact, but it senses your heat. A ripple of violet light flashes down its stalk and disappears. A greeting, maybe. Or a warning. You're not sure. This entire world is built around low-light living. Photosynthesis still happens, but only in niche forms. Some organisms stretch high on translucent stalks toward the sky, where the scattered corona of the hidden sun filters through cloud and atmosphere and planetary shadow. Others bury themselves, using deep-rooted structures to pull warmth from geothermal vents below. Still others are symbiotic, teaming up to survive. A crawling creature might carry light-harvesting algae on its back, feeding it with waste while gaining just enough sugars to keep moving. In turn, the algae collects the tiniest rays of light and stores them for days. Slow farming, living solar panels. You look up again and catch a glimpse of the gas giant itself, a looming curve of darkness that fills half the sky. Its shape is only visible by the rim of auroral fire skirting its horizon. The sun beyond it sends beams flaring through its atmosphere, bending light into stunning arcs. Sometimes those flares make it through, just barely, casting shimmering light across the landscape for a few minutes at a time. You witness one now. It feels like a miracle. The whole world pauses, the ground organisms stretch, vines quiver, the anemone pulses bright white for a heartbeat, and then it's over. The light dies again, swallowed by planetary mass, but the echo remains. You realize that to life here, sunlight is sacred. It's not the constant it is on Earth. It's rare, fleeting, maybe even mythic. Life forms might evolve to track and anticipate the next flare, building biological clocks around the gas giant's eclipsing orbit. There may be annual migrations timed not to temperature or seasons, but to light breaks, those rare moments when the moon slips just far enough out of shadow to glimpse the sun directly. And the organisms, they likely worship those moments, in a purely biological sense, of course. When the light comes, everything blooms. There are creatures that spend years dormant, waiting for a few hours of full-spectrum radiation seeds that only crack open after a solar flare. Mating rituals triggered by a narrow wavelength flash. Entire life cycles compressed into minutes of sunshine. Historians still argue whether such narrow windows of energy make complex life possible, but some suggest that conservation, not abundance, is what drives intelligence. In harsh environments, every action matters. Every risk is weighed. You can't afford waste. You have to plan. That's what you see in the larger organisms here. No frantic movements, no chaotic scrambling, just measured efficiency, a slow, deliberate rhythm to everything. You spot one now, a four-legged creature, tall and narrow, with a reflective membrane stretching from its spine to its head like a cloak. It moves in near silence, placing each foot with care. Its eyes glow faintly with tapetum-like structures, biological mirrors that maximize ambient light capture. It sees in layers of darkness that would blind most humans. It pauses at a ridge and looks skyward, waiting. You follow its gaze and realize another flare is coming. The sky glows behind the gas giant as the sun arcs into place. Not a full emergence, just a grazing burst. But it's enough. For 5 glorious minutes, light floods the upper atmosphere, illuminating the clouds in gold and lavender. The trees around you seem to vibrate. Leaves unfurl. The anemones pulse again. And the creature beside you opens its membrane, revealing tiny scales that catch and store light like living prisms. Then, just as quickly, it folds shut and disappears into the trees. You stand in awe and feel the stillness return. There's a fringe theory, of course there is, that such eclipse-bound worlds might host philosophical life, civilizations that grow not around domination, but reverence. Their religions might center around the idea of the unseen sun, the idea that even when light is gone, it's still there, just hidden. Their art could be light choreography, visible only during flares. Their technology might include biological memory structures, storing history in bioengineered organisms that bloom only under specific conditions. Their entire culture might hinge on a single principle: light is not constant, so when it comes, make it count. You lie back beneath the corona halo of the gas giant. The light has faded, darkness has returned, but somehow it doesn't feel empty. It feels full, like a world holding its breath for something sacred. The sky above you is dim, not dark, but the kind of dimness that comes with endings. The sun hangs low, bloated and sluggish, its edges feathered and fraying. It's no longer a vibrant orb of fusion-driven fury. It's a flicker, a final breath, a dying star. You're standing on a world teetering at the edge of stellar hospice care. This planet has orbited the same star for billions of years. It was likely warm once, rich with oceans and light, pulsing with complex ecosystems. Maybe civilizations rose here, biological or otherwise. Maybe great machines were built. Maybe forests whispered in breezes long gone. But all that is past. Now this place is fading, and yet not quite empty. The air is still breathable, barely. Cold, thin, and dry, like the tail end of a storm that never began. The surface is a cracked mosaic of frozen lakes, dust-covered plains and great petrified forests, trees fossilized in place, trunks like stone spires, leaves turned to translucent film. They don't rustle, they don't even sway, they just stand, as if waiting for something that's never coming. The light from the sun is ruddy orange but weak. There's little heat and less radiation. Photosynthesis is almost certainly a thing of the past. So what kind of a life could still exist here? You step carefully through a field of lichen-like crust. It crumbles beneath your boots with a sound like breaking sugar glass. But then you notice something. Movement. Not fast, not even slow, but deliberate. A patch of the crust seems to pulse faintly, expanding and contracting with geothermal rhythm. You crouch and watch as minuscule tendrils extend, almost invisible, reaching for chemical deposits in the soil. It's alive, just barely. This is end-stage biology. Organisms here don't grow, they endure. No rapid reproduction, no mutation-driven branching trees, just the last hardened versions of species that once proliferated wildly. These are the survivors, the final edit. Their metabolisms are so slow you could time them with an hourglass filled with syrup. They run on geothermal gradients, perhaps even nuclear decay in deep rock layers. They huddle in mineral cracks and under basalt overhangs, shielded from cold and space radiation that creeps in as the planet's magnetic field weakens. And underground, something more. You find a cave, a shallow one protected from the frigid winds, and crawl inside. The air is thicker here, warmer by a few degrees, enough to let you see the walls glisten with moisture. That's rare now, and precious. As your eyes adjust, you notice strange structures growing from the ceiling. Not stalactites, something softer, biological. They resemble heat traders, a speculative class of extremophiles that survive by capturing heat when they can, storing it in chemical batteries, and releasing it only when conditions become lethal. These might be the keepers of warmth, slowly sharing thermal energy with the organisms clustered around them like cold pilgrims near a dying fire. And then you see it, a creature. Faint, small, wrapped in a thick mineral-encrusted shell. It inches forward on pseudopods, absorbing tiny bits of fungus-like matter growing in the damp corners. It stops, vibrates slightly, then goes still again. It will likely not move for days. Historians still argue whether life can truly survive in a dying system, whether entropy's slow pull eventually unravels even the most stubborn biology. But some researchers point out that if organisms learn to scale their metabolism, to slow to the pace of planetary decay. They might stretch survival not for years, but for millions of years. Imagine a creature that lives for 10,000 Earth years, sleeps for 5,000, and wakes for one to feed, reproduce, and store energy, then begins again. Entire generations measured not in days, but in epochs. You exit the cave and climb a nearby ridge to get a better view of the land. Below you, the terrain rolls gently, barren now, but patterned with what look like ancient irrigation scars, long-dried channels that once brought water to fields, or to city-like structures whose outlines you can barely make out. Civilization was here once, or something like it. You wonder what their final years were like. Did they build deeper? Did they turn to geothermal energy? Did they digitize their minds and upload them to crystal memory cores buried beneath the crust? Or did they simply let go? It's possible that the last intelligent beings on this world didn't rage against the fading of the light, but watched it, documenting the slow decline, archiving thoughts in slow-ticking machines, whispering to the future in radiation-safe code. You sit and feel the stars light on your skin. It's warmer now than before, but only barely. The dying sun must have pulsed, shedding a final wave of energy like a sigh, a cosmic reflex. And for a brief moment the world seems to shimmer. Around you, creatures emerge, briefly. Flat-bodied, wide-eyed, low-energy forms that crawl from cracks and hollows to bask in this temporary kindness. Their eyes aren't for vision, they're thermal readers, detecting the faint uptick in warmth. They feed, some mate. A few rise into the air on membranous wings that catch the breeze like parchment kites. A final celebration, a final dance. You wonder, will they know when the last pulse comes? Will they feel the moment the star gives up and collapses inward, shedding its last light before shrinking into a white dwarf, and then, eventually, a black dwarf, invisible and cold? Maybe they'll gather, not out of desperation, but ritual. Maybe their myths tell of the final flicker. Maybe they sing during it, or glow, or maybe they sleep and never wake again. There's a fringe theory, one of the more poetic ones, that dying stars trigger something spiritual in their orbiting life forms, that civilizations at the edge of their sun's life don't flee, or panic they accept. They make peace with entropy, they fade gracefully. And maybe that's not extinction. Maybe that's an offering. You lie back, one last time, on the brittle grass of this nearly dead world. The sun pulses again, fainter this time, a heartbeat slowing, and around you, the last of the biosphere still breathes, still moves, still hopes. Now you're walking through possibility, not one world, not one sun, but a corridor lined with hundreds, no, thousands of them, stretching out like distant lanterns in the dark, each one with its own signature, its own orbiting mysteries, its own conditions for life that may or may not exist. You've reached the Goldilocks gallery, the part of the cosmos where real planets orbit real stars in that narrow band of not too hot, not too cold. And we're not speculating anymore. These places are real. You stand on a gentle rise overlooking a holographic array of known exoplanets, each one swimming through a projected sky in perfect time with its sun Kepler, 442b, TRAPPIST 1e, LHS 1140b, Gliese 581d, names that sound like passwords or serial numbers, but they are worlds. Some rocky, some watery, some strange, some hauntingly familiar, some close enough to reach in a few dozen generations, others practically unreachable, but no less real. And the question that keeps ringing in your ears is simple. What might be living there? You step forward, and the projection shifts. Now you're on Kepler 22b, one of the first potentially habitable exoplanets ever discovered. It orbits a star similar to our own, and it's just the right distance for liquid water. Scientists think it might be a super-Earth, with a thicker atmosphere and oceans that stretch from pole to pole. Imagine that. A world of endless sea, where life evolved not on land, but beneath gently sloshing waves. Not creatures with legs, but with fins, with hydrostatic limbs that push through warm currents, and phosphorescent coral towers. Intelligence here might never invent fire, but it might invent memory coral, growing colonies that store song, story, and history. Through neural fibre-like filaments cities grown, not built. The display shifts again. Now you're among the TRAPPIST-1 system, 7 rocky worlds, all orbiting a cool red dwarf in tight formation, like pearls on a string. Some of them are in the habitable zone, some are likely tidally locked, but the system is packed, and that opens wild new doors. What if life arose on more than one of them? And what if it could cross over? Interplanetary exchange doesn't have to wait for rocket ships. Microbial life could be flung between worlds by meteor impacts, spores drifting through space for centuries, evolution skipping across planets like a stone across water, or maybe one species learned to build, learned to float, leap, traverse. And maybe now there's a civilization spread across multiple worlds, each with its own culture, shaped by its star-facing or shadow side, but all rooted in a shared origin. What would a society like that believe? Would they see planets the way we see nations? Would they measure identity not by species, but by sunlight profile? Now the hologram rotates again, showing Proxima Centauri b, our closest known potentially habitable exoplanet. Just 4.2 light-years away, it orbits a red dwarf. Remember those? The kind with flares, tantrums, and slow light. And yet, it sits in the right place for water. We may find signs of an atmosphere here. Maybe even biosignatures, chemical fingerprints that hint at chlorophyll-like molecules, or methane, or something entirely unfamiliar. We might not see cities, but we might see change, order, patterns too deliberate to be chance. You crouch down in the simulation and touch the planet, triggering a speculative render of the surface. It's dim, windy, covered in basalt rock and low-slung plant life designed to drink every photon. The biosphere here would be quiet, slow, deliberate, but it would pulse with intent. And what if we sent a probe? What if it landed, cracked open, sent out a beacon and waited? Would something crawl over to examine it? Would something answer? You step back, the view panning outward to show the full catalogue. Over 5,000 confirmed exoplanets and counting, and those are just the ones we found by accident. Each one might hold oceans, skies, forests, beings, or nothing at all. But the point isn't whether life is common or rare, it's that the range of possibility is enormous. We've imagined life under red giants and rogue planets, in cloudscapes and in caves, on worlds with 3 suns and none at all. We've stretched biology into crystals, gases, and symbiotic colonies drifting through magma. And for every outlandish idea we've explored, there's probably something stranger out there. Life might not even look like life. It might be networks, patterns, resonances. It might be the absence of entropy in a place that should have decayed. It might be nothing more than a glimmer, a signal, a shadow that wasn't there a moment ago. It might be staring back. You watch as one last world fades into view. No name yet, just a designation. It sits in the habitable zone. Rocky, temperate, unknown. And your mind does the thing it's evolved to do. Wonder. You picture oceans, wind, songs, or silence, a windless world, a still sea, a place that's waiting not to be discovered, but simply to be understood. Because the final truth is this: we don't need proof to imagine, and sometimes imagining is the first step toward knowing. So now, take a breath. You've travelled far, across worlds that blister, freeze, float, fracture, and flicker beneath suns of every kind. Some dim and distant, others blindingly close. You've trudged across basalt plains under blood-orange giants, drifted weightless through thick cloud oceans, curled in the shadows of 3-star chaos, and stood silent under the fading pulse of dying light. And through all of it, one truth has followed you like a second shadow. Life finds a way to exist where it shouldn't, and if not life, then at least the potential for it. The whisper, the outline, that single possibility, however quiet, however rare, is enough. Let your thoughts slow now. Let your imagination roll gently backward through the gallery. Kepler's frozen sea world, Trappist's sibling planets, orbiting in tight embrace, the hot crystal sky biospheres, painted in ribbons of refracted sun, and that rogue world, alone in the dark, glowing from within. Not one of them promised comfort, none promised safety, and yet you saw them, alive in their own way, adapting not to ease, but to extremes. Maybe that's the point. Maybe life, in all its stubbornness, doesn't thrive because the universe makes room for it, but because it insists. So lie back. Let your mind float. The stars are out now, not just ours, but all of them, scattered like glitter across an endless velvet sea, each one holding a question. Each one maybe holding a story. Maybe one day we'll go, maybe one day we'll listen, maybe someone else already is. But tonight, just rest. Let your curiosity dim like starlight beyond a horizon. Let the weight of cosmic silence become soft and warm, and let the thought of distant skies somewhere out there be enough for now.